Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
Today we have a very special guest, somebody that I have been dying to get on the show for a very, very long time because since we started this project, I think I've been aware of his channel, See the Pattern, where Gareth Samuel explores myriad different open-ended questions inside of standard paradigms, which is something that obviously we love to do on this show. He does it in a totally different way. There are these very well-researched, in-depth analyses which distill down these individual theories or alternative ideas into short videos. And so it's a beautiful channel, and I've just really, really been wanting to sit down and chat because I feel like we would be great friends. And turns out that we are now. So Gareth is coming out to speak at our conference this summer, Beyond the Big Bang in Sesimbra, Portugal. And we had the occasion to meet up throughout the year planning this conference and thought we would sit down and just record a chat about all of our favorite theories and the way that science seems to be progressing, particularly cosmological science, fundamental atomic science, really all of your guys' favorite topics, mine too.
Yeah, Gareth has done a ton of work on everything from expanding Earth to dark matter and dark energy to issues with LIGO to issues with, Big Bang cosmology. And so this is a person who just has been exploring the same space that we spend a lot of time in. And like other conversations with people that are doing the same thing, it feels a little bit like coming home, where we spend so much of our time talking to people who are like, well, what if the Big Bang didn't happen? And then there's this entire process of trying to figure out how to reassure them that the world's not going to end if the Big Bang didn't happen. And then we find other people that are on our wavelength, and it's like, well, no, we can actually talk about all the other theories that are out there and all of the different pieces and how they fit together. And it's this really, I'm going to say electric, which is not intended to be a pun because he's into the electric universe, but I do think that it's this really beautiful and electric way to talk about the world, where it's not all the mysteries are solved. We're just, putting another coat of white paint on the walls.
Yeah, and Garrett's really comfortable with a situation where there's a theory that has some good ideas inside of it and maybe not all the good ideas inside of it, which is something that I think that we really lean into at this place. So I think you guys are going to love the conversation. I think that if you can find a way to make it out to Portugal this summer, you would love what Garrett's going to be sharing there. In other news, if you haven't already signed up for our new segment Paradigm Drift, once a month we're getting together and letting you guys present theories to us. But we give you only 60 seconds to make that pitch, and then we'll interview you for a little bit afterwards. But you can check out the link in the description and see if you have what it takes to convince everybody that you have a revolutionary idea that's going to change the world.
The next Paradigm Drift is already scheduled. It is going to be Friday, May 9th at 6:30 p.m. Eastern this time, which means 3:30 p.m. Pacific. We're going to be doing it live with one of Shiloh's oldest friends from Ohio. And so we hope that you will sign up because the last two have been a hoot.
Finally, remember, podcast is entirely paid for by you guys. That means that the reason we can put all this time and energy into it is because we have an incredible community of patrons over at patreon.com/DemystifySci. And honestly, you can make a huge difference with as little as 75 cents a week, which is probably nothing to you, but the more people that sign up to give us that 75 cents a week, the more time and energy we have for this project. And so it means a ton to us, and we get extremely excited when we see that we have a new patron. So make our day and make this project happen into the deep, deep future.
Absolutely. See you at the Sunday Salon. And for now, enjoy the conversation with Gareth Samuel of See the Pattern.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
Yeah, there's something about the human collective consciousness that just can't handle more than one general story. Right? It needs to be this linearized thing, I think, for people to. There's like something in our hardware, I think, that really forces us to be on the same page about reality in all of its myriad details. Otherwise, you just start feeling crazy. But also just the ability to simplify that down to this streamlined. And by the way, it's a super heroic story too, right? Like there are brilliant geniuses who come along and upend everything, and then that goes on for a little bit, and another genius comes along, and it's just this nice stepwise ascendancy of mankind. One genius at a time. It's just easier. I don't know. There's something very. It's ingrained in us, I think, to look at history this way in some sense.
But I think there's also a problem in that how those ideas were treated in the past is different to how they're treated now. And I think the problem is that there's more invested in theories. There's more riding on it, and therefore it's more important that the current consensus continues. And therefore, when they look at anomalies, often the anomalies aren't to falsify the model. It's more, how do we fix it? Yeah, and then you end up with a patch here, and then a patch there, and a patch, and it's not because they don't believe that there is an alternative model. It's more that it's easier to patch what you have than it is to have to. And the problem is, once you've got multiple patches, it's really difficult then to actually say, okay, if we remove all of this, actually, we could restart with everything new, and it looks like that. That's extremely difficult to do because all your data, all your models are based on that patchwork, and the way you interpret that data is also seen through the lens of your current model. That means that from that lens, when you look at something else, it doesn't look the same because you're not interpreting it through the same data or the same filters, the same models.
And it also seems like even if you jump ship to a new model, you're going to have to patch that model to some extent as well. Like there's no perfect, we're never going to perfectly model reality, right? Like a model airplane isn't a real airplane at the end of the day. And you can keep adding photo etched parts onto it to make it more realistic and stuff, but it's still just a model. And I think that that's really painful because now you have a ton of work to do. But at the same time, isn't that what science is all about? It's like doing work, and I don't know. It just seems like it's exciting too.
And people get paid money to do that, right? But I think the problem is it's sometimes easier to keep going in the same direction than it is. And as much as I hear people say, scientists are always looking to falsify other people's theories. And that's like, yeah, that's sort of true, but actually, is that really true in the broader context of whatever it is? Often they're talking about a small part of it, one part of their analysis that points out certain thing rather than the entire framework. And I'm not saying that the entire framework is wrong. And I believe what you say is correct, that it doesn't matter which model you look at, they all have inherent problems. I've not come across one model that you look at and go, brilliant, that explains. I mean, I suppose you could argue string theory has the potential to do all of that. The problem is the calculations are so immensely complex that you can't even make predictions with it. So, the idea and the concept is interesting, but that's true with a lot of theories. The ideas and concepts are interesting because they look at problems in a different way, but nothing is perfect. And I don't know whether that's almost the way the universe is meant to be, that it's meant to be this, you can never quite achieve whatever it is you want. Every time you try and search for a better explanation, the complexity of the problem goes up like a sort of fractal. You can keep diving deeper, you keep going, but there's just more to find and more depth to go. And yeah, you'll need more models to explain all of that depth.
I think so, and I think that's beautiful as a scientist. Like, I think this applies to art as well, but in science, like, people are often, especially novice scientists, are very scared of getting their ideas swooped out from under them and scooped and all of this stuff. But the super bosses are just like, I don't care because I'm an idea factory. Like, I've actually cultivated the ability to come up with ideas, not any particular idea, but like, I just have worked that muscle of generating new approaches to a problem, to the point that it just doesn't matter. I can just throw these things out all day, and that's pretty awesome.
I would argue that the society that we've built today is less inclined to come up with new and radical ideas. I think the way that we teach doesn't engender curiosity and doesn't engender a desire to want to fail and through failure to improve. I think but particularly in the UK, I can't really speak for.
Yeah, you were a physics teacher for a while, right?
Yeah.
What was that like?
Oh, I love teaching. And I guess that's why I love doing this as well. The idea of trying to get someone to understand what it is that you see, and particularly trying to explain in the form of analogies or other ways that they can conceptualize what it is that you're explaining. I love that part of it. That for me is really exciting. What I find disappointing when you're teaching is that you can't give students the freedom to properly explore, to properly do things and do them wrong. Like a lot of learning nowadays it's not about wrong. It's about you have to learn these things. And then you have to learn those things and you need to be able to do them in order and then practice it on this thing. Oh, but do this experiment. But make sure that when you do this experiment, you write the results down like this. And I don't want a graph that looks like that. And where's the learning in that? Yeah, okay, they've done the experiment. And you can ask them, can you recall that experiment? Yep. What did you learn from that experiment? Well,
Man,
yeah.
I had the worst experience in high school physics. Like I was really on my own interested. Like I was reading all of the pop sci physics books and everything. I was way into trying to understand how the universe works, but there's something about the way it was taught where the teacher kind of made it feel like all the problems had already been solved. And so by the time I got to college, I kind of wanted to major in physics, but I was just also just, and honestly, my advisor, they just assign you an advisor at college when you show up, it was a physics professor, and he also made it seem like everything was done, like they were just kind of, I don't even know what they were doing, just greasing the wheels at this point. But it took me many, many years to really confidently believe that that was not only not true, but could not be
Yeah.
more untrue.
Yeah. And that's a shame because I think that is, it's partly a reflection of the fact that this idea of constantly improving, this idea that society is always getting better, but that it doesn't want to admit that actually, you know what, these are not perfect. I would much rather that you teach, here's the Big Bang, this is the current consensus. It has issues. These are the issues, and then you explain the model. These are some alternatives. They have problems as well, and that's how you sort of group them together rather than. And it is, like you say, I mean, the way I was taught was exactly that. The way you teach it is basically that this is the model and this is correct and we know it's 100% correct. And people spout that, oh no, the Big Bang has been proved. You're like, well, really? How exactly has it been proved? What to you is proof? And that's a shame because I think it should be a much more open. I guess the problem is time, right? With all of these things, how can you teach someone all of those things and have enough time to be able to do it? And you can't.
What happened to you as you were teaching that made you start to think that perhaps the explanations weren't the explanations? Because there's plenty of teachers that go through it and, 30 years later are still teaching whatever the astrophysics textbook or the physics textbook says. Like very few of them seem to come around to the point of realizing
I think
that.
when you're in it, you're just doing a job, and you don't really have time to think about it because your pressures are not the greater thoughts of being able to understand how this fits into the greater picture. It's really, I've got to teach this class and I need to prepare that. I need to mark those things and I need to make sure that this is done for tomorrow. I'm going to prep that experiment and all those things. You're not thinking about the greater things. So for me, it was actually illness that gave me time out of it to reflect on all of that and realize that what am I doing? Why am I teaching these things that actually, it's not that they're not true, but it's not the way that we should be teaching children. And through the illness, I started the journey of this whole thing, see the pattern, and that's sort of how it came about, and that gave me time to reflect on a whole load of things, which I guess illness does for a lot of people. It's a moment of pulling out of reflection on yourself, and then realizing and starting to really study into some of these topics. Like I'd come across the whole thing started because I'd come across some videos from the Electric Universe conference, and it was actually Halton Arp. It was one of the talks that Halton Arp gave at one of those, and I was fascinated by this idea that there were these quasars and there were these objects that connected to them, and that there was this misunderstanding of what they are. And I kind of wondered how and why. So I started to dig into some of Halton's work. And then I also asked the question, well, this idea of the electric universe, how would that work? And what are the things that underpin it? which led me down the route of plasma cosmology and looking at Hannes Alfvén and some of those, and reading through all those papers, and that's sort of where my journey started along this whole thing, and it's a journey of discovery, because you realize that, okay, people discredit a lot of what Hannes Alfvén wrote, but actually a lot of the core of what he wrote is still applicable. He took some of it to levels that maybe are not necessarily that applicable today, but the ideas that he puts down absolutely still hold today. And it's funny because you see some of those ideas still reflected in some of the theories. Okay, they don't necessarily give him the credit for all of it, and they change some of the emphasis of what they look at. But in essence, it's still the same concept. The fact that plasma and electric currents play a significant role in shaping some of the structures that we see in the universe. And I still wholeheartedly believe that that's true.
I love how measured you are about that. I think that that's one of the markers of scientific discourse that I really respect and admire, which is that you look out onto the world and see things that may be possible and may be true and partially applicable, and it's this very active process of trying to figure out where to be able to place those boundaries. And I think that that's really the future of whatever rebirth of science is happening right now. I think that that is the thing, because you guys started talking about this idea of this patchwork,
Yeah.
where the current theories are just pieces that are sort of assembled and smoothed over in order to make some cohesive whole. And yet, like, you have to, that has to be kind of built into the system too, where you're like, well, no theory is going to be able to explain everything. And so I think that that's a really valuable insight. And I've always thought that you make particularly measured videos. Like, you're indignant about the fact of how absurd things are, but I think that it's also very measured.
I also love the way you simplified plasma cosmology just now in a way that I actually understood it better than I ever have, actually, when you said that, because you said it's all about. Okay, let me preface that by saying we just sat down to record a podcast with a plasma cosmologist with a plasma physicist who's actually going to be presenting at the conference, a last minute edition. Our friend named Patrick Van Reyes. And the funny thing, we're going to actually re-record the conversation because his thesis kind of boiled down to, and we didn't totally understand this till the end, which is why we're doing this over, that plasma is actually a state of matter that can in some sense be thought to occur at almost every level of organization. So there's liquid plasmas, gaseous plasmas, basically any conductive substance that's changed, physically its atoms have rearranged in such a way that it's now conductive, whereas it wasn't, can be considered a plasma. And so and I walked away from that conversation, I'm like, oh my God, what is plasma cosmology then if it's basically everything? But I think what you're saying about electric currents, and to whatever extent magnetism is involved in that, play an important role in the structure and the evolution of the cosmos. That's a really reasonable point, and it does seem to be somewhat sidelined by mainstream analysis. Like, I don't find a lot of talk of such ideas in my mainstream astronomy text.
No, but that's because of exactly what Hannes Alfvén warned about, which is the whole magnetohydrodynamics idea, which, to be fair, he worked on, because part of the reason, and it's funny, this is a recurring theme in a lot of things I look at the moment, is the models that we use to simplify. The problem is that in the day, to do the calculations on because essentially they're like an n-body problem, right? You have all these plasma particles, positive and negative charges, and to work out collectively what's happening with a whole cloud of these is computationally too difficult. So therefore, you look at a way of being able to abstract it, which in a nutshell is what magnetohydrodynamics does. You treat it as an object, and then you deal with the forces that apply to that object, in a sense, right? Which means that you don't talk about currents because you're talking about the general thing. And what Hannes Alfvén warned about was that although it's useful to use that abstraction, if you remove totally from the fact that there are these currents that flow that create the magnetic fields that you are looking at, then you're losing an abstraction layer which gives you information about what's happening in that substructure. Yeah, it's not necessarily saying that all of magnetohydrodynamics is wrong, because it's a useful tool that you can use to model, large clouds of particles in a simpler way. But that doesn't mean that there isn't a current flowing. Like, in order to, this whole idea of, for example, that you can bake in a magnetic field is one of the concepts you have in magnetohydrodynamics, right? That the magnetic field exists, but that there isn't a current. But that's because you treat it as an entire thing, right? But there must be a current in it that maintains that magnetic field. It's just a different way of looking at it. Yeah, you're either looking at it from the outside, a macroscopic view, or you're looking at it from a microscopic point of view. And the problem is, with looking at it as a microscopic point of view, it's incredibly difficult to model. Yeah, you would have to model all the positive and negative charges within that. But that's essentially what he was pointing out. That's a big danger in how we do it. Which is why, when you look at large scale structures, well, no one talks about, because they don't see that there is a current that flows. They don't see that those magnetic fields are created by something else. And I get that there is this notion that generally, when you look at a plasma, that charge will attempt to equal out, this point of it reaching sort of
hear that one all
equilibrium
the
points.
time. Yeah.
Yeah, which kind of makes sense. Like, you wouldn't want to stay in that position for a long time. So then the question becomes, okay, well, if in the plasma universe you end up with these massive filaments that are created, how do they come about? You would have to have a potential difference that's driving that current from one side of the universe to the other. And it's actually, Peratt has a really nice way of explaining that. And he sort of points out that imagine that you had a cloud of plasma somewhere, and you had a magnetic field that's there already. Something else has created this magnetic field. You can then argue, well, okay, well, what created that magnetic field? But let's for now say that there is this magnetic field, and this cloud starts moving. There is a velocity that this cloud has through that magnetic field. That then creates a force on those charged particles, and they will start to flow in two different directions depending on their charge. So this is how he explains, and he works out in his book. He works out the size of the cloud required and what potential difference that would drive, and how big these filaments would become. Because, again, coming back to the idea of stories, and the idea that we as humans like to have stories that have a good narrative. And you look at the Big Bang, and it's a good narrative, right? It starts from the beginning and gets bigger. Okay, you can argue about how it ends, but we're sort of happy with that story. If you look at plasma cosmology, it's a bit of a different story, right? Because what is the story? And this is part of the problem when you look at the static state universe ideas, or an infinite universe as well. You don't answer the question of, well, where did it come from? You end up with this, it's always been there. And what I thought was particularly interesting about Peratt's model is essentially what he's saying is that that's not necessarily the case. What we see as the universe around us is a short-lived temporary event. Imagine that one of these giant gas clouds has moved through a pre-existing magnetic field, created these filaments that it ends up as like a plasma sheet, which starts then twisting into filaments, and then it cascades downwards. You end up with filaments that intertwine, and where they sort of meet and connect, you end up with pinch points, which forms the galaxies. And he had a whole model for how that would be explained, which is why you end up with galaxies forming in clusters. But eventually, that downward movement, the cloud sort of stops going through there. It stops, it dies, it ends. And then somewhere else, maybe those magnetic fields leave a residual, which maybe in the future then creates a secondary event for another. So it's almost like, it's not a Big Bang, but it is like a creation event.
It's like a
followed by a
cyclic kind
death.
of universe.
Yes. And it's funny because Hannes Alfvén also wrote, although he had a very different model of the universe, because he worked with Klein to come up with his own theory of, and where you would essentially still have a Big Bang, but it would be this antimatter matter concept that he'd have. But he did write about the idea that essentially double layers could form like a pumping action. They're a way of being able to dissipate energy but drive movement. So you're converting different types of energy. And he saw that plasma could be moved from one area of the universe to another through these mechanisms. It didn't really necessarily describe what the point of it was, but what he was saying is that you don't necessarily see, even if you're just dealing with gas clouds, or plasma clouds, they wouldn't be static. That over time, small fluctuations in charge could lead to small currents, which create filaments which move charge from one area to another. So you'd end up with this material being transported slowly, but over. And of course, if you had a higher current driving it, you would have more movement. And he certainly liked to describe things in terms of circuits. He liked to see that there was a connection between things, and therefore there would have to be a return current in his idea of the system. Perhaps it's slightly different because it's a cascade event where you're going from one thing to another, and then you have to sort of, almost like a waterfall, you have to bring the water up back to the top and then let it fall down again. And that might be somewhere else, but that's sort of his model of it. And then Lerner again is different again, and they all fit within the umbrella of plasma cosmology, and that in itself creates a problem because, and I'm not saying that any one of them is wrong or right, but people then look at it and go, well, there isn't a consistent story. Well, it's not necessarily that you have to have a consistent story. They're just approaching the problem from different directions.
Yeah, we've convinced ourselves that science has to have this one monolithic story that covers everything. And I think that that's a grand disservice to the project of trying to come up with models that are effective for helping us think about what things are causing it. So like as you're talking about these different models, I'm thinking about what Shiloh said about Patrick's perspective of plasma being this state that matter is forced into. And so what's moving is partially the gas cloud, but it's also partially this higher abstraction layer of what's actually how the material is being induced to behave. And so all of a sudden what you're talking about is you're talking about the transfer of dynamics as well as the way that those dynamics then cause cascading events downstream. And this connects to another conversation we've been having with a friend named Michael Hughes, who's studying the biochemistry of water. And he's starting to realize that water is the signaling molecule in the sense of its state information being transmitted. He's like, the way that water will organize around a protein can be dissipated into the bulk structure of water, so you have this momentary reorientation of the water molecules that then passes like a wave through the substance in order to be able to communicate something across the length of the cell. And so this idea of, the universe is enormous. And so if you have all of these dynamics that are occurring, the magnetic field emerges from the dynamics that are outside of the system that you're looking at. Then as the system evolves and it forces changes in the way that things are positioned, it creates a different magnetic field. And so it just feels like this eternal passing of state information back and forth to create new disequilibria that then have to be dissipated for the next phase to begin. And I love the idea that these things parallel one another at scale. And through thinking by analogy, you can start to understand why perhaps it's not a conventional circuit. Because to think of the universe as having a conventional circuit seems overly simplistic somehow, or it asks these weird questions like, well, what is the circuit? Where is the ground? Where is the power source? And then you have this strange, centralized, almost designed system, as opposed to being something where
I don't think he necessarily saw it as a circuit for the universe. He was describing that things are in closed loops. So he had a model for the aurora, which was a closed loop. He had one for the sun, which was a closed loop, one for a galaxy, which would be a closed loop, and then the idea would then be, if you looked at filaments, that they too would have their own sort of, and within it you might have smaller. So it's like a modular sort of system. But he was always looking for, when he looked at, whether it's a star or whether it's uh, like a filament or other things that might dissipate energy, he was looking at how to describe them in terms of part of a circuit. So he would look at trying to label them as whether it's an inductor or a motor or something like that, trying to find ideas of because essentially they are energy converters, right? There's no denying. It's just a question of whether you're considering it to be electromagnetic energy or whether you're just considering it to be gravitational energy, which is then dissipating it in radiation or other forms. There isn't, like, again, when you abstract to a different level, the idea isn't that crazy. Like, we already do it, but we don't really think of it in terms of a circuit. The problem I always have, and equally when you look at the electric universe, is I think the term, when you use electric current, it drives people to, well, that's like a circuit, right? That's like those wires I've got over there. That's, we don't have that. I don't look up at the stars and see, well, there's a little wire there. Like, so people are put off when they hear those ideas. Whereas that's not necessarily what you're talking about, because in a lot of these, the flow of that charge would be quite a subtle thing. It's not like this, you'd put your hand in, oh my God, I'm dead. I've been fried with a billion amps worth of charge. That's not what it is. It's just a different way of carrying energy, whether it's, particles in a gravitational field or whether it is charged particles flowing through a magnetic field. There is an exchange of energy. And that's basically what you're talking about. It's just a different way of looking at that problem.
I think those guys did a really good job, the Electric Universe folk, at some point of identifying that sometimes current can flow and it can be completely invisible. Like, there's different current densities which result in that luminiferous arcing, right? Sometimes you get lightning bolt looking stuff. And Patrick is going to go through all these different pieces with us. But you have this dark mode too, right? So there's ample opportunity for, invisible actions to be occurring, especially when all we have in astronomy is light. It's really easy to miss stuff that isn't generating light or heat or something like that we can easily observe.
Yeah. Yeah.
So that leads me to wondering if you have a good sense of the history, why plasma cosmology became not really part of the story that we tell today.
Well, he pointed out one really, I was blown away by this. You pointed out that they essentially bake in the magnetic fields. And that's crazy, right? That's worth restating. So there is no real necessity to consider current flow in the Hans-Alfvén magnetohydrodynamic.
I think the problem was at the time when because Hannes Alfvén and Anthony Pratt, more, I guess, Alfvén than Pratt, stemmed from the era which is after the Second World War, where they were doing experiments on essentially like nuclear bombs, where they were looking at the plasma that they can generate and the conditions under which that occurred. And they were studying that behavior of the plasma. So he worked in Los Alamos, as did Anthony Pratt. Anthony Pratt actually worked for Alfvén for a period of time. But the problem is, at that time, the Big Bang had already been verified as, verified in quotes, but people are already buying into that concept. So coming along with a completely radical idea was, at that point, already started to be an uphill struggle. And the fact that he had worked on magnetohydrodynamics and essentially sealed the nail in the coffin for himself, then tried to undo it in his acceptance speech for his Nobel Prize, it was too late because people weren't listening. We have those tools and we will use those tools. Thanks very much. And we'll just take that and run with it. And I think from that point onwards, it was extremely difficult. And it was only really him, Pratt, and then Lerner as well, who were working on those models. Now, there are other people who still study it to an extent, and I think there's probably interest in other countries in some of those ideas as well. But yeah, it's always going to be that debate in terms of trying to undo a model that is seen as successful and is where the money is going at the time, that's where money was going, to prove relativity, to prove this, to prove that. So therefore, when someone comes along and says, well, actually, we've got this, and remember as well that Alfvén's initial model that he proposed with Klein was almost like a mishmash between the two, which then didn't really work either. Like it wasn't, and there wasn't enough in it in order to propose an alternative model. I would argue that Peratt probably went the furthest in terms of coming up with a story that fits it, and then Lerner more on the side of trying to undo what the Big Bang did, so trying to undermine that. And they're all slightly different angles, and therefore I think it just never really, because you're talking when you're talking about sort of the 1980s, 1990s. That's really
that
when
I think is a really, really powerful piece of the story, is the lack of consistency. This, by the way, this happens in this happens in protest movements too, right? So a lot of times ineffective protest movements will split their agenda. Like everybody, like the Occupy movement was like this. People with every single complaint under the sun ended up showing up, and eventually there's no core values really, or like no core agenda even, right? Except for everything sucks. And so there's something about mainstream movements and mainstream institutions where they derive a tremendous amount of power from unifying their talking points. Like everybody's standing behind one consistent story, and it's really easy for people to get behind it because it's simple, it's streamlined. There's a cohesive energy. It's a big team.
There's money. Let's not forget
money
that.
follows, right? I mean, it's a powerful platform to have a unified vision of what you're all fighting for, and you have a lot of people behind it, and you can attract money. And
I would say that that's a fundamental law of the universe, though. Like, that's how you accumulate power and influence across the board in anything that you're attempting to do. If you have any institution is built on a cohesive set of goals. And often it also includes a cohesive set of methods for achieving those goals or preferences for solutions. And so it seems like science as a tool for society to rally around in its ability to tell complete stories about the universe requires everyone to kind of more or less agree on the story that's being told, because how do you live without that?
Well, yeah, I mean, I would be quite comfortable with knowing that there are patches that you've only got part of the knowledge. So in fact, I would probably be more comfortable with that than having a veneer gloss over the top that makes it seem all shiny, nice. But as soon as you scratch the surface, it's like, oh, hold on, there's a massive, great big hole there. Why is that? Shh, we don't talk about that. Just put it back down and let's not talk about it. And I think
if you're trying to figure out a coordination problem of how to allocate government money, then you start to filter along the lines of what is somehow technologically effective or somehow lends itself to this big group effort so that you're spending money effectively, because you don't want somebody to pull up that you've funded somebody who's saying that, the universe is actually the brain of a fruit fly that we're all living inside of, and none of it is real. And just there's a ton of politics involved in what it is that you fund. And so we talk about this a lot, where the minute that you start to have massive funding projects, billions of dollars being spent, it begets this requirement that the outcome is a cohesive, coherent consensus that everyone can kind of pat themselves on the back for saying, well, we have pushed the frontiers forward, we have arrived at our new understanding, and we will go forth with this because we spent $10 billion on it, and the alternative is impossible.
Yeah, it's like the Large Hadron Collider. We've got to this point now, and we've discovered a lot. Now what we need to do is spend even more money because we want to do bigger experiment. And it's a constant sort of thing. I don't disagree with your analysis. I think in terms of the way governments allocate money, that's a clear problem. Like you can't allow, or they don't allow people to have the freedom to think outside the box, which is why you end up with sometimes the heretics are those who don't really care. They're at the end of their career, and it's like, yeah, fine, if you're going to fire me, whatever. But they're almost all gone now. Like, I don't know what the next generation is going to be like. I don't know whether that will continue or whether it will be a different set of fish, and whether the rules will be even stringent, even more stringent, and restrict people from saying too much or looking beyond their, like, the problem I see, and this is a deep rooted problem, is the silo mentality, that people become experts in the letter K, and all they know is the letter K, and they're not familiar with the rest of the alphabet. They're so stuck in their way that that's all they see. The problem is that unless you have a clearer picture that actually there's an entire alphabet, and in fact, if you combine those letters, you can make words. That sometimes to me is lost in terms of when you look at some of the problems that we have in science, and then you can start to see there are bridging gaps between some of these missing pieces that actually, if you slid something else, would actually solve some of those problems. And as an example, an ether. Yeah, it's something that supposedly we got rid of. Yeah, Einstein disproved the whole idea of the ether, even though he actually did later say that actually, it doesn't necessarily rule out an ether. But you look at some of the anomalies we have, then actually the idea of an ether becomes a more attractive thing. And if you look at some of the wording of the things that we now explain, you kind of look at it and go, that's kind of an ether, really, isn't it? We just call it something else, and it's not really an ether, but really it's an ether. And that's kind of a bit weird, because it's funny, because from the whole talk that you had on the CMBR and the background radiation, and the tired light model, like if you look at tired light, what is one of the biggest problem of tired light? You can't find a mechanism. There isn't a coherent mechanism that can explain how light loses energy and isn't scattered, right? Well, there is, but it's just that in order to accept it, you have to accept an ether. I don't know
You
if
have
you're
to have
familiar
like a material conception of light to begin with to understand why it would lose energy in an elastic reaction.
Yeah. Well, the funny thing is, when you look at quantum mechanics, it states that once a packet of light once a photon is created, you can't alter it, right? It is in that state forever. And it sort of stems back to Einstein's photoelectric experiments, where he shone light on it, and it didn't matter if he shone a low frequency light. When he increased the intensity of that light, nothing came off. It was specific to the frequency, not the intensity. And therefore, the idea is that proves that light is quantized. Now, I would argue that doesn't prove that light is quantized. What it proves is the structure within which the light is being emitted takes on a quantized structure, the atom. Yeah, we know that atoms have electrons in orbitals that are quantized. They can only exist at certain positions, and therefore when they fall back, they emit light. Well, obviously they're going to then emit it based on that jump, which is quantized, because it can't be in between that. But when you look at something like, so the idea from that stems that you can't change a photon. A photon, once it's created, stays as it is. It's a bit of a problem when you look at cosmic background radiation. So how do they get around it? Well, okay, we'll just, the universe itself stretches, right? Light is created with a particular length scale, and that length scale it somehow knows, and therefore when the universe expands, it expands with it. So we don't have a problem, because it's not the photon that's stretching, it's the universe. The universe's length scale is stretching, so therefore it looks like the photon is different, but actually it's not. Okay, so that's a clever way of getting around that problem. But when you look at other
Doesn't
things,
seem that
like,
clever to me. Sorry,
well,
breaking physics doesn't seem very clever to me. I would have gotten an F in my physics test if I'd tried that one.
I disagree. I think it is a conceptually clever way of solving the problem, because you effectively, because if you don't do that, then the problem that you have is, well, where does that energy go? What you're effectively saying, there is no energy change. It's just from where you're standing, from your perspective, at this length scale, it looks different. But when that photon was created, its length scale was really, really small. So therefore, its
But like,
photon,
what does that even mean? Like that what does that mean for a length scale? Like, I don't like go to make coffee and the length scale of my coffee pot changed, and like that's not how physics works in reality. That
yeah, but
doesn't
we're only
ever
talking about
happen.
photons here. We're not talking about material. So this is, again, it's the
Exactly.
clever way of describing it. It's like what you're basically saying, because a photon has a relationship with space-time, which when it's created, yeah, it always travels at the speed of light relative to space-time. Yeah. So therefore, when it's created, the universe has a length scale, right? Which the equations give you. And therefore, as the universe expands, the length scale gets bigger. So therefore, a photon that's created nowadays looks different to a photon that was created in the past at a different length scale. When you go and get your coffee, the length scale of the universe hasn't changed, right? Not
I mean, I get it. I
significantly.
get it. I get that it's clever, like the same way a Ponzi scheme is clever or something. I'm just like not too
I,
impressed by it. That's all.
I think
I'm
that
not
it's
saying that I believe in expansion. What I'm saying is the way that they explain cosmological expansion, it's a clever explanation because it removes the problem of the energy. You're not saying that you're losing energy to something. What you're saying is it just looks different from your perspective based on changes in the universe.
and I think that it's clever because it reflects some innate human understanding of the fact that things are different depending on how long ago they happened. Like if you drop a rock into the pond, the wavelength is much, I think, much larger at the place where the rock drops, and then as the wave spreads, the wavelength changes. And
Yeah.
so you can see that there's these systems that, from the moment of being set into motion, when you're observing it later, it looks different. And so I think that what it was an attempt to take that intuition about the nature of systems and to codify it in this kind of spectacular way of, the rippling of the universe and its fundamental.
Well, I think the problem is that the if the interpretation that the redshift is due to motion, which is essentially where Hubble started, right? The interpretation was its velocity, so you end up this nice little straight line graph. That creates a problem because if the objects are actually physically moving, that has other implications. So by actually saying that it's the universe that expands, it fixes part of that problem because it's not the objects don't have motion. They have motion relative to each other, but it's just the universe that expands. So it's and again, it sort of stems from Einstein's equations, but again, it's the metric that you use to interpret Einstein's equation. So like we are specifically talking about the metric that has expansion. Like Einstein didn't design it. Like his original idea wasn't that there was expansion. It was a static universe. And it's funny because when you look at the history of all these changes and modifications, it kind of it's strange how we've ended up where we are with the patches that we've had to introduce to keep it going. And like
Didn't
this
he
whole
call
idea
this
of
expansion didn't he call it like the biggest blunder of his whole career or something like that?
the yes the yeah the because he used it to keep it static. So it was almost the reverse of what it is. But there's an irony in the whole dark energy thing as well, which is it almost it beggars belief when I look at it because it's just so nonsensical, right? The idea is that we build this if we believe that redshift is related to distance, uh, and that the universe does expand over time, and that you end up with this stretching. Fundamentally, what that means is that redshift is linked to the expansion of space. It's a one-to-one relationship, right? The more you stretch it, the further an object is away from you. So it means there's a direct relationship. We build a distance ladder based on Cepheid variables and S1A supernovae, and from that we calibrate, and we assume it's a linear relationship because that's what it tells you. So why would we expect that there would be a difference? So the weird thing is that in the 1990s, there were problems with the it wasn't the lambda cold dark model, it was the cold dark model at the time. And what they wanted to try and do is verify. The idea was that the universe would be slowing down. Yeah, that there was enough mass that it would slow down, and then the question was whether it would just perfectly stop and not move anymore, whether it would contract back in, or whether there'd be a little bit more motion and it would just continue on, but at a slowed rate. So how did they think that they were going to measure this? So they were going to observe supernovae, and what they had expected to find is that based on the luminosity measurement that they could make, and there's a lot of calibration issues that are involved here, but that this supernovae would be closer to them than they had predicted. And what they actually discovered is the opposite. It was fainter, it was further away, and therefore what it meant is the universe was accelerating. But no one asked, why would there be a disconnect between distance and redshift? At what point does it become acceptable to actually say, actually, at this point, I'm going to disconnect my length scale. I'm going to allow the universe to move a little bit more, and then I'm going to stick it down again. Because it either means that everything else that you did before then was incorrect, or it means that your idea of length, expansion, and stretching is wrong. Like, none of it makes any sense. And what's even stranger is the speed at which it was then accepted. Like, when they discovered it and they worked it out, we're talking a new fundamental force here. There's some force, dark energy, that is expanding the universe. It's not a small thing. It's expanding the entire universe, right? So you'd think there'd be a little bit of, well, do we really think this is true? You know, could there be something else? Might it be a calibration issue? Might there be something wrong with our understanding of redshift and how we measure distances? No. Pretty much overnight, that's it. Bang. Dark energy is born. We accept what it is. Why? Well, there were problems with the cold dark model. And one of the problems was essentially that when they looked at the large scale structures based on their models, there wasn't enough time for those structures to have formed. But if we have dark energy that's accelerating the universe, that fixes our problem. And there were several other fixes as well that having dark energy and accelerating universe fixed for them. So you fix more problems than that troublesome thing that you have to accept, and therefore we continue with it. And this is part of the problem, the idea of that you're fixing things, you're constantly looking at anomalies, and you're not questioning, why is there an anomaly? You're almost saying, well, that anomaly, well, that probably means this, so we'll fix it because that solves those things. And that's a problem, because then if you now look at the expansion history, it's not this, as Edwin Hubble draws this diagram, this nice straight line. It's accelerating, so it's curving upwards. Where still, if you go back and look, the whole inflation period creates another period of rapid expansion. So from that, you can conclude that at no point is there actually a linear relationship in terms of that expansion. So either you accept that redshift is baked in intrinsically in that expansion, and therefore it doesn't matter if it accelerates or decelerates, the redshift will always match. Or you say that actually we have to decouple it, and there's some problem with how we analyze redshift, because you can't
and
have
how
both.
we analyze light in general. I mean, I think that if the problem is a misunderstanding about light, then it's a totally different silo of people who are capable of addressing that problem. And so you're working in a situation where your tools don't allow you to address what you need to address. That's really crazy.
Well, the problem, coming back to light and coming back to an idea of an ether, if you look at simple things like reflection, how do you explain reflection if you have a photon that you can't change, right? You can't change any of it, and it's a particle, right? So if you look at the way quantum electrodynamics explains it, there are a number of different ways to explain it, but essentially, the explanation is not an explanation that gives you a how. It just tells you that it is. So the idea that you have all these paths and only the ones that are exactly at the angle of reflection reinforce itself is kind of like, yeah, but that doesn't really explain how. Like if you look at classical explanation, then it's a boundary condition, right? And it's a wave, and the wave reflects off of it. If you consider light to be an ether, the same thing, you can consider that a reflection. It's light is nothing more than energy traveling through a medium, and it's therefore reflecting off a boundary condition, and it'll reflect off perfectly. Compton scattering, right, is another example of a strange behavior. Essentially what you have is light coming into an electron, and the light loses energy, so it reflects, it changes, it scatters, it changes its angle. So as it comes in one angle, it'll go out at another angle, but will have reduced energy, and the electron is imparted some energy. So it's like a recoil, it's like a collision, although not quite a collision, right? So you can't explain it by the fact that the electron absorbs the photon, because there isn't actually a time delay between those two things, because then you would expect it to absorb it and a little while later emit it, and it doesn't actually do that. It's an instantaneous event. So again, how does quantum electrodynamics explain it? Is there is an interaction as the photon approaches, there's an interaction with the electron, and essentially, in a nutshell, the original photon gets destroyed and a new one gets created that points at the right angle, right? Again, it doesn't explain the how. It can correctly compute the angles and the energy loss and all of that, but it doesn't tell you why it happens. And again, if you go to the idea of an ether or a medium, then you can explain it, because then what you're dealing with is the fact that you essentially have like a glancing blow off a particle, a resonator in that medium, which is what an electron is, which is absorbing some of that energy. The wave continues, but obviously it's because it's interacting with that resonator in the medium, some of the energy is removed, and it's sort of bounces off it at an angle. So you end up with a sort of a reflection type principle. It's more like a sort of a glancing blow. So
I
again,
think another piece of this puzzle comes to do with neutral atoms and so forth, because a lot of the way that these equations treat light as being this little magical particle thing, the result of that is that it seems to pass through atoms, right? Like we're told it doesn't interact with neutral hydrogen, for instance, as it travels across the cosmos. It's probably more reasonable to think that it is a less lossy relay reaction. Like it's certainly not just magically jumping through the atoms that are in front of it. There's something happening, because that's how physical reality works. And so you have to actually start reconsidering what it means, for light to be transmitted. And, reflection is another great example of that. But you also, there's a lot of atoms in between my eyeballs and your screen right now that I'm talking to you, right? And I don't imagine that the light is just magically going through the atoms. Like there's some sort of transactional process happening. It's the only rational way to explain what's going down.
I'm not sure about that, because if there was a transactional thing, then there would be such a delay between.
I don't think so. I mean, I also don't think like you don't have a delay in a material that's extremely stiff, right? Like the material, there is a delay. It's at the speed of light, first of all. But if the atoms are all and the medium are made out of the same material, then the delay is evidenced as the speed of light. You're just essentially talking about these relay instances.
If you consider that there is an ether and that the light is passing, light is not a thing. The light is just a perturbation of that medium. Then what you're saying is correct. That that wave does pass through the neutral hydrogen atom. But just as in, if you look at atoms, if the frequency of the photon, of the wave that's passing through, isn't enough to stimulate the electron, then the electron isn't going to do anything. When you look at atoms, they are, I think, very special conditions with bound states, which means that the electrons behave differently to free electrons. If you look at like Bremsstrahlung, for example, you can create energies of any type, the photon that's emitted as the electron accelerates or decelerates. But in orbitals, you're restricted to these particular quantized orbits. And orbits is probably the wrong word that we use, but it's the easy way to sort of explain it. You have a transition point from one to the other, and when it jumps, but
I
it
mean, you
means
see
in
the
order for
same
it,
thing in any resonance system, right? Like
yeah,
any object that you
exactly,
vibrate is going to have harmonic modes to it,
yeah.
on
Well,
which you can additionally amplify those modes with specific frequencies that are commensurate
yeah,
with it.
and
But
there's no
that doesn't mean
reason
that
to.
it doesn't absorb energy, but with other frequencies, it certainly does. It just doesn't result in harmonic resonance. Like it won't amplify the signal into a new mode unless
Yeah.
the frequency is matched perfectly.
Well, stimulated emissions is another example of like essentially what you end up with is an electron in an atom which is already in an excited state, and then as as a photon comes by, then it essentially makes a copy of that original. This is the the current explanation. A photon copy is made by that excited electron as it falls back down, which matches exactly the existing photon. So therefore, you duplicate it, which is lasers. That's stimulated emission. Laser light is produced in that way. But if you think of in terms of a resonance system, then what you end up with is this idea that actually that electron is sensitive to the vibrations in the medium, yeah, and it can either stimulate or absorb the energy from that medium. So what happens is if you can get the electron in the right state, that when a wave passes by and it's resonating at exactly the right frequency, then it can enhance the current wave and actually bump it up. So you end up with a double amplification of that same thing. It isn't two photons, it's just one photon with more amplitude that you've created. You've enhanced the signal. It's which is sort of essentially what you're saying when you talk of the idea that other atoms interact with it. They might interact loosely, as in it's just brushing by, I'm not going to do anything, or like in stimulated emission, where it's in a certain state that actually you can bump it up, or Compton scattering, where it's actually drawing some of the energy out. Yeah, I think when you look at it in terms of an ether or a medium, it presents a much cleaner way of explaining some of these things, I think, in terms of the way light and potentially it applies to other things. Like I don't know if you're familiar with Tom van Vlaanderen. So he was an American astronomer. He's written. I actually have his book somewhere up there. Many books on. It's quite controversial in terms of his ideas. He talked about the exploding planet hypothesis. His idea was that what we call the asteroid belt used to be a planet that exploded. And he calculated based on the orbits of the comets where that originated from. So he did all this incredible work to actually work out that it would originate from what we now call the asteroid belt. And one of his theories, he was particularly interested in Lesage's gravitational ether concept. But he had this idea that actually there was a dual ether. So there would be a light ether and a gravitational ether. And that actually there was an interaction between the two. So that light that traveled vast distances would interact with that gravitational ether and energy would be drawn out of it. So the idea of tired light could be explained through the idea that energy is being removed from the wave as it travels because it's interacting with other material or ethers. It's not material, but other ethers. And in his case, it was gravity. And he had a very interesting loop that he was able to draw between how you would go from one ether to the other. That was like a recycling system that he had, which culminated sometimes in exploding planets.
So you said something really
Can
interesting.
I ask you a question really quick
Yeah,
about the
go ahead.
exploding planets?
Sure, yeah.
Are Vesta and Ceres supposed to be the moons of that planet? the really rounded asteroids that look like moons?
I'm not
That's
sure
okay.
that
That's
he
okay. That's
went
okay.
that far in his theory. I think he
Okay.
was more looking at the orbits and the angle of those orbits of the comets to work back where it came from. Like he's in his book, he writes a beautiful description of how orbits work and how if you want to change orbit, the actual dynamics of what you have to do. One of the best descriptions I've ever seen of because it's not intuitive if you want to
I'll check
change
it out.
orbit.
Yeah,
Yeah.
it's interesting. I didn't mean to interrupt you, Nastia. What were you gonna say about the ether?
What was the guy's name? Tom Van Flandern?
Yeah.
Excellent. Okay, I'll make a link to it in the description. I was going to ask you about the ether. You said something really interesting that you called it a material and then you corrected yourself to say that no, it's the ether.
Yeah.
Lay out the way that you think about that.
Because the idea is that, like, if you look back at the original ethers, it was a lot of them were mechanical ethers, whether it be cogs or wheels or some sort
Vortices.
of elastic material that vibrated and the problem is people have this idea that when you start describing it as a material, well, a material of what? Or what is it? Uh, and I don't think that's necessarily an important part of understanding it. Like if you look at Lesage's gravity concept, essentially what he described was that what is gravity is actually all these very small particles that we can't see that travel at immense velocities, many times faster than the speed of light, and they collide with all things, right? And it's those collisions that create the force that we see as gravity. And in fact, it's an opposite force, right? You only feel that force if you remove it, or you shield one side of it. So a planet and a moon, let's say, the moon is almost shielding part of that constant cloud going around it, which means it feels a force inwards. And it's a very clever way of describing how gravity works. And in fact, there are many papers that people have written actually being able to explain many of the like Mercury's orbit and all those things they can actually explain using Lesage's gravity. It also explains why, for example, galaxies rotate the way that they do because it falls off at a certain distance. There's so much noise that you don't get that constant feel. It is a very local force that acts within, whether it's 2 or 3 solar system range forces, but it falls off. The force. It's not a constant force that continues forever. So it's in his world. It's those small particles. Now they don't just then you go, well, what are those particles? Where do they exist, and why don't they interact? Why can't you see them? But I guess that's no different to saying that there are quarks. No one's seen a quark. We don't know that they exist. Yet we're quite happy to accept that they're there. So, yeah, with all these things, like you said, nothing is perfect. And I think what you have to look at is whether you can connect some different ideas together in a way that actually can explain more than the problems that you perceive with the model itself. And I think that's where Tom van Plunderen has done quite an interesting job in connecting some of these ideas together and creating a framework that can explain multiple things at once. It's not perfect, and he goes off in all sorts of other tangents that are probably not helpful. But that's often the problem with these. You find there's like a core idea, you kind of go, that resonates with you, that makes sense, that absolutely. But then they keep going. You're like, no, you should have stopped. No. And
What were you gonna say?
I was gonna say, it just occurred to me that we've been hearing this push gravity thing a lot lately. Actually, it just occurred to me that couldn't you test this with a Cavendish type experiment by putting some hyper dense material in between the two bowling balls?
Majorana, I don't quite know how to say his name properly. He conducted experiments. He had a similar sort of idea based on Lesage's model. And if I'm correct, and it's a long time since I looked at it, he was one of the people that was one of the first to verify the speed of light, or he built very accurate experiments to test the speed of light. So what I'm saying is his skill at producing experiments was extremely high. He was well renowned for it, and he had this idea that you could create this shielding, that if a Lesage model was correct, that you should be able to shield for it and you should be able to detect it. And he built this intricate experiment, and he claimed that he was able to find this idea that he could effectively shield gravity. Problem is that when other people reproduced it, they were not able to verify that finding, and yeah, since then people sort
I've
of
seen a
discredited.
few. I haven't watched these videos, but every once in a while I get a YouTube video on my feed that's like somebody reproducing the Cavendish experiment. It would be really cool if one of those people would just take a huge piece of lead and stick it in between them, like something with like a commensurate density that should be able to accomplish said shielding, like to any measurable degree. That would be a game changer.
Yeah, it like a lot of it also depends on the model as to whether there is a substance that can effectively shield it without it just appearing like it's a massive object. Like you could say, well, the moon, the moon absolutely shields it, but yeah, it's so massive that it creates also the effect that we know is gravity. Like you can't distinguish the two. And I don't think in Lesage's original theory that he speculated that you could shield it. I think his idea is it would just be an effect that you needed enough matter to be able to stop the particles.
But couldn't
So
that be
it's
a
about
density thing
volume.
if it was based on mass? If it was based
Yeah,
on the
maybe.
amount of matter, right? You should be able to make a material. You could have two balls, like your globes, and they could have a lower density, and they should still exhibit some attraction in the Cavendish experiment. And then you take a hyperdense material that's very thin and shield it, right? So your densities are matched still. So there should still be
So the
same.
masses are matched, but the density's not. Yeah, so you have the same mass, so therefore the
Yeah.
same force.
I gotta think
the
about this some more.
density.
Yeah.
I know what you're saying, right? So you would have something that is dense enough that you could shield it, but then the problem is that it would be a smaller object versus something that is less dense but bigger, but the
Yeah.
same mass. So you create the same.
You still
But
have the
then
mass imbalance, but the distribution of the mass might be different in such a way,
Yeah.
like it should be able to shield it, but it doesn't necessarily have the same attractive center to it necessarily. I don't know. Is that possible? I have to think about this some more. I don't know. I've always just wanted to like identify a great experiment to test this push thing. And the more I hear about it, the more I'm like, this seems like
well, look
something
at it, Majorana. Like if you look
Okay.
him up, he did a lot of those early experiments trying to prove that you could shield gravity,
Cool.
but wasn't successful in terms of people didn't accept his results, despite him being a meticulous experimenter, well known for it. Those results, they were like, no.
That's a really common feature. So we had a guy on the show who I think we're going to put out this episode next week, Adam Forrest K. And he wrote a book called Escaping Shadow Physics, or Escape from Shadow Physics. And it's all about this hydrodynamic analog for quantum mechanics, where you can take silicone droplets and then float them on a bath of oil that's being vibrated, and then they produce these shapes underneath
Pilot
them.
waves. The pilot
Exactly.
wave. Yeah.
Exactly. And so what they did is they were actually able so Adam would say it's not exactly pilot wave theory because of the dynamics that are involved in it and the fact that the system has memory, so we went down this rabbit hole with him. But basically one of the labs was able to reproduce the double slit experiment using this system. And it's very delicate because the temperature in the room has to be just right, the depth of the water bath or the oil bath has to be just right, the frequencies have to be just right. And so they were able to do it in the laboratory, but nobody else was able to reproduce it. And so I think that this is a common feature of figuring out a system that lets you test something that it's very delicate, where the next time that somebody tries to reproduce it, some variation in setup or some small change in the designs that isn't recorded anywhere in the lab notebooks or in the protocols will make it so that the reproduction is almost doomed to fail because it's just so finely balanced in order to be able to see the thing that you're looking for, where it makes me almost feel like the axiom here, the rule, the basis should be to think reasonably about whether or not it is possible as the basis. And it's like, okay, well, if it's hard to prove that this is actually the case, that's kind of almost fine. as long as you've followed some rules for a parsimonious explanation where you haven't introduced, dark matter or dark energy or things that you can't see or mysterious particles that are moving around. And with push
Breaking
gravities,
physics.
breaking physics, yeah. And with push gravities, I think that for me, I'm like, well, what's the source of these things? What's the source of the little bundles that are flying around? It just seems like you're adding something extra to provide for the effect, where then you have another level of inquiry of, okay, well,
But
what's the
along the same
source?
line, like if you maybe not gravity, because I suppose you could argue that gravity is the shape of space time. So let's just go electric. So we know that an electric charge creates a field, right?
Mm.
So what's the field?
Well, presumably the field is the influence. So, okay, if you have an ether that is
No,
the
no, 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 no.
product
Without an ether.
with
So if you in terms of just a classic explanation, like because
Well, a
you're
field
worried
is
about.
just a set of vectors whose quantity varies with time, right?
Okay,
It's
but if you take
essentially just measurements or predicted measurements.
take a magnetic field can store energy. Where is that stored?
well, that's the whole problem, right? Like that premise doesn't make any
Right.
goddamn sense.
Yeah. Yeah.
Like the
So
concept of energy makes no goddamn sense without
it's
actual material doing something or in potential to
yeah.
do something.
In essence it is a sort of ether, right? It's a different concept. It's not necessarily, but it's an abstraction that we find acceptable because it's just a field.
Well, it's a
But really,
mathematical ether. They're literally like, look,
yeah,
there's a thing that we can detect that's doing stuff, but it's just literally this platonic essence of force, and there's no body, there's no object, there's no motion that's causing it. It's simply this weird thing where we like put our probe into empty space and there's fields and the fields are the thing, and you're like, why did you do that? Because the whole point of the hydrodynamic quantum mechanics analogy is so powerful because the mathematics of the way that the droplets behave in the bath are identical to the mathematics of wave functions. And there's many problems in saying that what's happening at the quantum level is the exact same thing that's happening in the bath, because obviously they're different. And yet, there's a philosophical step that you can take there, which says that if you have mathematics that are explicable by virtue of it being a system in motion that has components that are doing things, that produces the forces in question,
In other words, a physical system can
Yeah.
do this.
yeah.
there must be a physical system that is doing the thing at the foundation of the universe.
We should at least
Yeah.
go looking for it. It's at least we know it's possible for like a physical system to do quantum mechanical activities, right? It's not impossible.
And so I think that there's such a fundamental fracture here where it's like every single person that we talk to, almost, except for a couple, accepts this idea of forces and fields and mathematical particles as being the foundation of physics.
Yeah.
And there's even the craziest people that we interact with are like, yeah, fields, man. And I'm like, how did this become so hard baked into reality where we don't ask the question of what has produced the field? What is the field doing? Because all that it's telling you is it's telling you that there's
More like what's doing the field.
yeah, what's doing the field, because it's basically
Yeah.
telling you that there's some kind of interaction that's happening between all of the like the way that we think about it is, okay, a field tells you how a point particle will behave when placed into the field. And I'm like, well, obviously what you're really looking at is you're looking at the walls of your system. You're looking at the borders of your system, realizing that they're creating some kind of influence on what you then place into the system and watch move. But we're so preoccupied with, well, what is the prediction of that motion, that the question of like, where does the field come from? What is setting up this system? How does it all fit together is just like people look at you like you're insane. Like you think people treat you like you're insane if you start talking about ether. The minute that you start talking about like, well, what's causing the field, it's basically they just think you're an idiot. They're just
Yeah,
like, oh, you're just so dumb. You don't understand. It's just fields.
yes,
That's
just
so
accept
cute.
it. It's a capital F, by the way, not a little f. Oh, okay. Yeah, I kind of feel that we ended up going down a rabbit hole um, just after World War II with a lot of things. A lot of things we ended up making decisions, and the way that funding then worked for a lot of those projects meant that people were incentivized, is maybe not the right word, but that they essentially had to keep doing what they were doing, keep producing the same thing, and therefore it just kept building on that. And some of those original ideas of do we need fields? You know, is an ether a better description? They never circled back to it, even though Einstein had said essentially, you know, you still have sort of an ether in the whole space time concept, but people don't really talk about it. People don't talk about Einstein's alternative view that actually light itself could actually be variable. And I find that quite interesting because essentially it describes the whole curvature of light in a totally different way within his theory. You know, it's essentially that gravitational fields, and it comes back to this idea of gravitational field interacting with light, that it is that interaction between gravity and light that essentially slows it down, that causes it to curve in Einstein's alternative view of that. And that, yeah, again, we never come back to it. We just accept that's the version. And in the same with the Big Bang, that's kind of credited with Einstein, but really it's the Friedman whatever metric that is used to get us to the expanding universe model, which is plugged into Einstein's equation. So yeah, and it's presented as if it's just that way. And I think also back to this whole problem of people being siloed doesn't help that bigger picture thinking, because people are only incentivized to look at what it is that they're tasked to do. I have to keep going with this thing, and I have to produce stuff that is in relation to this, rather than thinking about how this might connect to something way over there. I mean, there are people that do that. That, you know, no denying that there are people who try and break those boundaries. But the more silos you get, the harder that becomes, because you're not talking about uniting two silos. You're trying to unite multiple silos together. And that's extremely difficult if you're trying to uproot it. It's the same problem when you're looking at overturning an existing paradigm. There are so many patches and other things that are connected to it that it makes it extremely difficult for you to pull it apart, because you have to explain all these other things in a way that your model can, and that's extremely difficult, because when you first start off with a model, that, you know, you can't explain everything. There's no one that comes up with a model that suddenly explains absolutely everything in the first go. It just doesn't exist, and it might well get some things wrong. That's like, again, is that a bad model if part of your model doesn't work properly? And I would say no, it's not. It's just it's a work in progress, and people then judge you by that one thing that doesn't work and then reject the rest of it. And like I said, sometimes it's the gems that you find are the bits in that model that actually resonate, and that you can actually see different things coming together, but no one gives you the opportunity to do that. And that's a shame. And yeah, I think also creativity is something that often is lacking as well. I think you have to be able to think in ways that are not standard, in ways that are not normal. Like, if you don't do that, if you don't imagine the what ifs, then you can never get to a position that actually you can come up with something radically different. And I think the way that we teach students, the way that society works, is that's not something that's encouraged. We want you to do what it is. You are letter K. You will press that letter every time I ask you to, and you will not do anything else, please. Yeah, got it?
Pardon the interruption, but I have to ask you for a favor. If you were listening to this conversation and you were enjoying it and you want to figure out how you can support the podcast, think no more and come over to patreon.com/DemystifySci. You can give us just 75 cents a week, which is not very much at all. But through the power of large numbers, you will be able to power our project into producing better and better episodes, which means being able to record conversations in person, which means being able to throw more live events, and which means helping the world change through the exploration of brand new theories. I'll see you at patreon.com/DemystifySci. Do you think that there's a mismatch between the topics that you're most interested in and the things that do best on your YouTube channel? That's totally unrelated to the conversation overall.
I'm not sure. I, I find it sometimes difficult to predict what will do well, and sometimes things that you think should do really, really well, then they don't. And then you produce one, and you're like, it just explodes, and you're like, well, why was that? Like, so I don't think there's necessarily a link between the two. I think I certainly think in terms of what I do and how I do it has evolved significantly over the years that I've been doing it. And I think the problem is that more recently I've been spending more time finding those nooks and crannies, pulling things apart, and I really do enjoy doing that. But it does take more time. It means you produce less stuff less often. But that works if they're then more popular. I mean, oddly enough, the one that they released 2-3 weeks ago has been extremely successful. You know, looking at the structure of the atom. I like Ido's model of the structured atom, and I've always one of the problems I've always had with it is can you reconcile it with quantum mechanics? And I know that Ido always says, no, it's clean slate. You have to remove everything, and I'm like, well, I can't. I mean, a bit like the discussion we had. It's extremely difficult to do that. You know, that's a journey that you have to go on. And for a long time, I'd done the original videos explaining Sam based on the book and based on conversations that I'd had with him. But I always felt there was more, like, because I kind of feel that it's difficult to engage with the topic of Sam from an outside perspective. Obviously, you're always going to people who naturally sort of gravitate towards something that's different. But if you want to engage with it from the perspective of, you know, could this be a viable alternative? What are the barriers to doing that? And I think part of the barrier is how you would explain some of the problems in a quantum mechanical point of view. How do you? So that's sort of I started the journey, which is where the whole Lena series that I did started from. Because the idea is that Sam potentially could explain Lena in a much simpler way than other models potentially could. But then as I sort of developed through that, I was kind of like, well, okay, but now I want to really understand how can we explain an electron in a nucleus. You know, that doesn't, you know, if you look at the normal equations, it doesn't make sense. You can't get that to work. So that was the journey that I kind of set myself on. Let's try and go down these rabbit holes and see if there is a way that actually, by pulling it all apart, that I can get it to work. So the first step in that journey was, well, is there actually structure? Is there evidence in when we look at isotopes and elements that the charge radius deviates from what we would expect? And indeed, when you look at that, it doesn't really make sense in terms of the normal explanation. If a neutron is neutral, why does it have such a significant impact sometimes and then sometimes not on the charge radius of an isotope? It doesn't necessarily make sense. And now I'm just finished. It's not uploaded yet. One that's looking at quantum chemistry, and once you start going down to quantum chemistry, now you really start to break open the problems in quantum mechanics. Not problems, but the limitations. And I think this is like, if you look at, often people say quantum mechanics is the most successful theory we've had, right? And then you look at it and go, well, that's extremely difficult to compete with, and you can't simply say we're going to knock it out of the way and have something else. But when you start looking at, well, what is it successful at, and what is required to get that success, then you realize that actually you have to add other patches onto it to get it to be this successful model that we see. You know, it's often portrayed as electron orbitals flow naturally from Schrodinger's equation. Yeah, they do for hydrogen. Can we do it for other atoms? Well, no, it's too complicated. Right. Okay, so then how do we get to this idea of, it does absolutely predict quantization, you know, from the equations. So it's not that it's wrong. I think part of the problem is that what doesn't naturally flow from those equations is structure or purpose. Like the whole idea of electrons transitioning does not naturally flow from those equations, from the wave equation, from Schrodinger's equation. It doesn't give you that. We have to impose that based on observations. We see photons being emitted, and they match those quantization levels. So it makes sense that that's probably the mechanism. But it's not to say that that is the mechanism, and it's not to say that the equation gives it. So this, when you look at it, I mean, you start looking at quantum chemistry, where actually we can do even less, and we have to put more constraints on the model to actually get it to work. What you realize that quantum mechanics is extremely good at predicting probability distributions, giving you a system and explaining where things might happen, but not necessarily how they happen or why they happen. And certainly it doesn't naturally give you structure unless you sort of poke it and force it to do it in the right way. So in molecules, you have to then impose the Born-Oppenheimer approximation to get structure to come out of it. You could argue they have been able to model it on simple atoms in a few cases purely from without the Born-Oppenheimer. But in reality, they still had to put constraints on it because computationally it's still too complex to do. So I would argue.
What is the Born-Oppenheimer constraint? I'm not familiar.
So basically, if you consider that everything has a wave function, and the wave function describes a number of different parameters, right? So it would look at the Coulomb forces, and there may be other, like in the nucleus, obviously there's the strong force interactions, and other forces, spin coupling, other things that you might want to model. So in a simple view, when you look at a hydrogen atom, it's a one proton and one electron. So computationally, there are two particles. So it's relatively simple to solve. There are just two bodies. One interacts with the other, and the other interacts with that one. Simple. Problem is, if we now go to a molecule, so let's take H2, we have 4 quantum particles. The problem is that each particle interacts with every other particle. So it's an n-body problem. And it becomes computationally, it's not impossible, but it's extremely difficult to do. Particularly if you're modeling it with more than just one force, it becomes unsolvable almost. So the problem is when they first introduced this, they didn't have the computational power to do it. So, it's brilliant. Oppenheimer and Born said, well, how can we want to do this? We want to be able to calculate it, and we can't. So we need to make some sort of approximation. So the assumption was actually, let's treat the nucleus, the molecules, as not the molecules, the protons and essentially the nuclei that make up the molecule is fixed. We're not going to consider them to be moving. They will have a fixed structure, and then we'll solve for the electrons and then deal with the nuclei themselves. So simplified the calculations, allowed them to do it, and gave them approximations that sort of worked. It matched what they saw in terms of the results. Ever since then, that approximation is still being used. Now,
is that kind of like you're giving it a ball and stick shape to begin with, and then imposing that on the downstream calculations?
Yeah, essentially, yes. In a nutshell, the bond angles don't come from you're imposing it on it in order to essentially put the equations through and get back what you perceive to be the structure. But the reality is, you had to enforce structure to get structure back out of it.
Got it.
Now, when they, like I think in the 40s and 50s, when they had enough computational power to be able to do it, they then attempted to do it full non-Born-Oppenheimer calculations, and they couldn't. Well, they could do it, but it actually didn't yield any shape. It just ended up being these amorphous probability clouds that had no structure, no bond angles, no structure, nothing like that. So they had to continue using the Born-Oppenheimer approximation in order to be able to, in terms of, from a quantum chemistry point of view, bond angles are extremely important. And the structure of the atom and where particular elements are in that structure is crucial to, like, you imagine a carbohydrate, which you just swap the hydrogens and the carbons around randomly. It just wouldn't work. So in chemistry, the location of things is extremely important, and they weren't getting that from those equations. Now, as I said, in more recently, they have been able to do simple molecules using less approximations. I would argue they're still having to do some approximations, but it's now less. the problem is it's an unsolvable. The one you know, if you look at in terms of chemistry, you're really dealing with chemicals that have many atoms that are part of it, and the problem is that makes it extremely difficult to solve. You would argue almost impossible.
And you have these like hybridizations, right? So you have like partial like moments where the molecule is experiencing one shape, and like I remember looking up water's molecular orbital description at some point. It was like 52 different hybridized orbitals, and I'm just talking about the valence like end of things, right? And so it spends all these times, these different moments, each electron's like kind of spending some probabilistic time in one shape, essentially. And it just becomes, and this was just one group's best guess, right? It's not like everybody agrees on these exact 52 orbital hybrids either. It's like that's their best computational attempt at it.
Is this an artifact of the time domain that we're examining something being so large relative to the time that it spends in any one conformation? Because we're talking about a molecule that's moving, right? Like if you have a sugar in water, we draw the neat little like hexagon planar structure of it, and we're like, well, that's what it should look like. But in reality, like everything is just kind of going crazy. So would you really not expect there to be some aspect of that where when you're integrating over even, a millisecond of probability, it's occupying this amorphous state, but if you were able to bring that down to approach a zero time interval, you would get closer to what it actually looked like?
I'm not a chemist, so I don't know, but my understanding would be that the bond length and bond angles, they vibrate, yes. So a bond can vibrate between it. It's not like they move position or swap over. They stay where they are. You know, the whole structure might vibrate, and that's a way that it can store energy. And there might be rotational movement and twisting movement that can occur, but fundamentally it retains that shape, and that is critical. My understanding, again, I'm not a chemist, is that structure is critical for when you're looking at reactions, because you have particular parts that will react, that will form new bonds at a particular location, and that's all to do again with where your electrons are and how they then bind together. But it's a combination of both, right? It's not just the electrons. The electrons are determined by where the atom is and what type of atom that is, and whether there are free spaces and free electrons that they can give up, whether it's an ionic bond or whether it's a covalent bond.
And so when you say that they solve the equations of these n-body problems and they just get these amorphous
Well, they don't
results.
solve them. That's the problem. They can't solve them. An n-body problem is intractable. You know, you can't. It's too complicated, particularly when you're dealing with a number of particles in chemical systems. So you have to make approximations and assumptions. But the problem is that means that fundamentally you're not dealing with those original equations, because you can't deal with all these particles, and therefore what you're representing is not the true quantum mechanics, I would argue. And the point more is that if you look at molecules, you have to impose structure on it to get it to work, right? In terms of electron orbitals, you have to impose some order in order to match it with what reality is, which is this idea that you have transitions that electrons move. Yeah, that doesn't naturally fall out of it. Yeah, it gives you the shape, the electron orbital shapes, but only for hydrogen. Like beyond that, we make the assumption that it is the same for all atoms, and it might well be. Like I'm not saying that that's wrong. And then when you look at the nucleus, then the same thing applies. But now when you look at the nucleus, the assumption is that there isn't shape. All of a sudden, we can abandon shape and we can just say it's all to do with energy levels. You know, that they sort of structure themselves. Well, they don't structure themselves; they order themselves in terms of certain energy levels or certain shells that might be filled. So the shell model and the nucleus model, but we don't necessarily impose structure. And kind of what it shows is that quantum mechanics is extremely good at predicting behavior where the system doesn't have to have shape, where we don't necessarily expect it or want it to have shape. That doesn't mean it doesn't have shape, yeah, but it naturally doesn't like to predict structure or shape. And I do wonder whether essentially quantum mechanics is not being used, or that we're expecting it to do too much when we want it to give us structure, and in fact it can never do that.
Okay, well, axiomatically, if quantum mechanics is a probabilistic interpretation of an event, and expecting a probabilistic interpretation to give you the shape of the thing that caused the event is insane, right? Like,
Well, for all of this comes down to like this strange irrationality where even the electron is a vibration, like it's a dynamic occurrence in and of itself. And so you built a house of cards out of events, and it's like you can't build a house out of events. Like I can't build my own house out of events. It can't be conceived that way.
Okay, so like in terms of the probability thing that I'm thinking of, if you flip a coin, you have an equation that tells you the probability of heads or tails, right?
Yeah, it's not going to tell you what it is.
It's not going to tell you what it is, and it's not going to tell you what flipped the coin or anything about this system that went into producing the moment that you're trying to describe. And so I feel like what I'm getting from what you're saying is that there's this set of mathematics that tells you really well about the likelihood of outcomes. And from that, there's some sort of break that prevents you from being able to go back and say, well, okay, this is the shape and behavior of the system that produces the probability, which I'm like, that might be inherent to probabilities.
Yeah, and I don't think that's necessarily wrong. What I'm not saying is that quantum mechanics should do that, but what I'm saying is that they're almost expecting it to do that. And therefore, when it doesn't give that, sometimes they go, well, that's fine, that's the nucleus. And then sometimes they go, well, okay, it doesn't really, we can actually observe molecules, and so let's now impose structure on it. So it's like this, when we see it and it doesn't match it, now we have to fix it. And when we can't see it, then we're fine to accept it as it is. The problem is that evidence is now starting to mount that actually maybe the nucleus does have structure, and therefore do we have to therefore impose structure on that model? Like, it's not necessarily that quantum mechanics is wrong, I'm not saying that, but it's the idea that quantum mechanics tells you all these things. That's what I think is wrong. It doesn't tell you all these things. It describes the behavior of systems extremely well. And from that, we tend to think that means that we know that this is the way that it is. And what I'm saying is,
it also kind of assumes this top-up construction of everything too, which I think is really interesting, right? Because it's like you could study a symphony and be like, man, this is beautiful, and it has this, we could call it a shape, but it has like a tonal palette to it, right? And it's has a form. You can experience a symphony or a rock band or whatever it is that you like to listen to. But then if you tried to just study sine waves, to understand how sine waves somehow resulted naturally in the construction of the symphony, you would never ever get there, because like the symphony is constructed based on different principles than just pure sine wave dynamics, right? You have the interaction of all the different tones with each other. You have these, discord, and just it's messy and beautiful, but you can't necessarily study all phenomena just from the ground up. Like that might not be the best way to understand the organization of the structure.
I'm also remembering now when we talked to Ito, I think we came to the same place where we were sort of like, well, surely the mathematics of quantum mechanics are describing something that is robustly consistent and deserve to be folded in some way to whatever new paradigm we're developing. And I was really amused where Ito said exactly what he said to you, which was like, no, clean slate. Like, we begin from scratch. And I'm like, they've done a lot of work.
And this, I think, is the problem. I think the problem is when people talk about quantum mechanics, I think it's so broad, there are so many aspects to it. And I think in particular, there are certain aspects that you can question more than others. And the idea of wave functions, I think, is an elegant way of describing some of these systems. It works and we can model it. And it's not that we can see the wave function, it's just a way of describing it. And actually, it kind of fits in with this idea of an ether anyway. The idea that I know it's not quite entirely the same. We're just describing several parameters in terms of a wave. But to me, it's sort of, I'm not against that idea, and it sort of fits in with that concept. And the fact that you can create equations that describe how that evolves over time, and probabilistically we see that happening. Yeah, there's no denying that that's part of it. The problem is this idea of many different types of particles doesn't naturally flow from some of those original principles. Again, you have to look at where does the original quantum mechanics come from, and how did we alter and add to that. So the idea that you have even the strong force, I would argue, like for me at the beginning when I first look at Sam, I was like, how do you really justify getting rid of the strong force, right? That's quite difficult. And how would you, even ignoring how you get an electron in between two protons, let's say that you can do that, and I now understand how you can do that, but let's assume that you can do that. How would the forces balance that actually those two protons don't repel each other? And the when you actually do the maths on it, actually it's the simple idea that the electron is essentially like a point particle. It isn't quite, because obviously the idea of point particle is an abstraction. There's nothing that can necessarily be a point particle, but it has very small diameter, right? And we know that the proton has a radius, 0.84, 0.87, depending on how you look at it, femtometers. And the idea is you stick this electron between two protons, and now you have an imbalance between those forces, because the idea would be that the when you look at a proton, the charge, essentially from the analysis that you do looking at the charge distribution in a proton, it isn't even. It isn't evenly distributed across the entire surface. In fact, when you look at the charge analysis, it's concentrated in the center, and then it falls off, but it falls off quite rapidly. So you can treat it as not quite a point particle, but very close to a point particle that has a barrier, that has a distance from which it sort of acts. Yeah, so the electron sits, let's just arbitrarily call it 1 femtometer, just to make it easier, 1 femtometer away from one proton. And then there's another proton that sits on the other side. So the two protons are 2 femtometers away from each other, but the electron is only 1 femtometer away from each proton. That creates, when you do the calculation, a net inward attraction. Yeah, because the electron is closer to the two protons than the two protons are from each other. And when you do the calculations, because that would be a deuteron, that idea, proton, electron, proton. If you do the calculations for the binding, the force that binds those together, it gives you almost exactly the binding energy of a deuteron. Now, is that a surprise? Is that a coincidence? Yeah, possibly it's a coincidence, a massive coincidence in my thinking. But effectively, one thing that you've proved by saying that, now there is a whole stability issue, but one thing that you've proved is that the binding energy is enough and does match observation of a deuteron. And that system itself does create an inward pressure, an inward force that we equate to a binding energy. Not the strong force, but an electrostatic binding energy.
Really quick. I know that you have a question. Hold on. Remind me how this ties into the structured atomic model. It's been a long time.
So the structured atom model is essentially you don't have a strong force. Instead, you have a neutron is a proton and an electron, but they tend to stabilize in configurations that are proton, electron, proton. So a PEP. Yeah.
Got it.
And you build structures from that. And so if you remove a neutron, then obviously it decays, and it would decay into a proton and an electron, which is also what we see.
Yeah. Okay. Go for it, Shiloh.
I mean, the piece of it that still leaves me wanting is what the heck is a proton? What is an electron? And why do they love each other so much? Like this, the force doesn't structurally emerge from this description for me.
But well, why does the structured atom model have to describe what a proton and an electron are? I mean, there are interesting questions, and I do agree, but that's not like I mean, quantum mechanics doesn't tell you what an electron is. It just tells you it is
Oh,
an electron.
so this is actually, I think, a really interesting piece, which is that one should expect that a theory, if we already have a theory that works really well, like quantum mechanics, which like the mathematics of it works and there's like some pieces that are missing, and so clearly like something's not quite right, you want a theory to replace it that answers more questions than the previous theory does. And so if we accept that quantum mechanics doesn't tell us why protons and electrons are attracted to each other and simply deals with forces and probabilities and fields, I think that it's reasonable to expect that the improvement upon that theory would allow us to clarify those questions somewhat.
But there's a fundamental difference here, because you're arguing that you're falsifying a theory based on the idea that the theory has to explain essentially what it considers to be fundamental particles. And I'm not sure that's...
Oh, I'm not falsifying it. I was just saying like a piece of the puzzle that still, in both of those models, there's just a little loose end there, which still leaves me wanting.
I don't disagree. I do often wonder whether the idea that, and it's a bit conceptual, but that essentially that the proton and the electron are actually were once the same thing, but you separate them and they always have this want and this need to be together. And the argument would go that, do you ever find an electron that doesn't want to find its not necessarily its original one, but a proton somewhere in the universe, that it's always fleeting from one nucleus to the other, always constantly trying to find, that you can never... And it's an interesting thought experiment. Like if you took an electron and you separated it, I don't know how you do it, you separate it entirely from the rest of the universe, so it couldn't see or connect to any other proton, would it decay into something else? Does it
Would
only
it
have
even be
stability?
possible? I mean, right? Because if they're just equal and opposite, I mean, it's easy to see them at least as being two motions of the same substance at different places. Essentially, like if you have a right, so you could start to work towards solutions like that. And I'm not like trying to like, I'm not like kicking Ito's model at all based on this. It's just something that pops out as like, oh, well, I wonder how we could work towards a more material model using this structure as well.
I think that's exactly right. And I also think that if you were to take the electron and you were to remove it completely and put it into a vacuum where there was nothing, I think it would just decay into the fundamental substance.
Yeah.
Like you would basically discover the unstructured ether would emerge from that, because it seems plausible that electrons and protons and all of these particles are some kind of resonant motion.
Yeah, you might actually find that as soon as you cut it off, it disappears, because, like you say, it's no longer connected to whatever it was that gave it energy. I mean, one of the things that if you look at an electron, a muon, and a tau, essentially in current particle physics, they're different particles. If you look at a muon, it decays into an electron and some other exotic particles or energy. The tau, the same thing as well. They all fundamentally carry the same charge. And what's the difference between them is their mass energy. And I kind of wonder whether actually they are different vibrations of the same thing. This idea of what is mass, like what we call it mass, like is a resistance to motion through a field, and is that created through the fact that actually it's vibrating at a different frequency and therefore it's harder to push it through. Now the electron, if that is true and the electron can be pushed into those different states, it's not happy in that state, because the muon decays very quickly and the tau even quicker into an electron. It's not a stable configuration. We create, the tau is only ever created in particle colliders. Yeah, the muon is created in cosmic ray collisions in the upper atmosphere, but it only lasts a very short period of time. So again, high energy that somehow imparts energy into the electron, and maybe it is, going back to the SAM model, an inner electron that is already in a different vibrational state because it's kind of stuck between these two protons, is imbued with all of a sudden with this extra energy, and then takes on this higher vibrational mode becomes a muon for a limited period of time, and then because it's unstable, it doesn't like being there, decays back into an electron.
What are you gonna say? I can hear the gears turning sometimes.
I was just thinking the neutron's another really interesting piece like that, which you could give a similar treatment to, or at least play with ideas about how the same, let's say, knot of material in motion could take on different states, because neutrons obviously decay into some of these other, particles, but they could just be motions of the same material, which are
I would
observed,
argue that a neutron decays into a proton and an electron. Yeah, you can
which
argue
is a hydrogen,
neutrino,
basically, right? Plus, like a
right?
little bit of extra leftover juice.
Yeah, if we go back to the SAM model, is exactly what you describe, right? You can argue that they'll say that's neutrinos, but I would argue we don't directly detect neutrinos. Neutrinos are an inferred thing.
They're the leftovers, right? There's some
Right, it's
leftover
the
juice
energy
in
we
the
can't
system.
exactly we can't account for, and that again comes back to this problem of when we interpret stuff. There's a lot of data that is provided as evidence, but actually is inferred. We don't. It's not direct evidence. It's inferred evidence. The Big Bang is full of it. Yeah, there's very little direct evidence. A lot of it actually is inferred, and then they infer based on the inferred data, and then they build models which are based on that inferred data to then analyze other data that is used to bolster the model, and so it continues, and it creates this idea of almost being unfalsifiable, because all this data that you have to then try and replicate that you can't replicate because it is all processed through the lens and the model itself, which if you stick your data in, is never going to match it, because you haven't built a model that is an expanding universe with all these patchworks on it.
Does this tie into the thesis for the talk that you're going to give at the conference with respect to the unfalsifiability? Or
yeah, so the fact that I guess it's part of it is the fact that a lot of it's inferred evidence, which is not necessarily a problem. Like, I'm not saying that you can never use inferred evidence, but you have to be more open about the fact that it's not direct evidence. And the problem with anything with cosmology is you quickly have to start inferring, because we have so little information available. But also it means that when you classify that this is the data, then you have to be able to understand that thing that you call data is actually inferred through a model. So, for example, the SN1A data that tells us distances, right? The idea of, you can't just look at a supernova and go, oh, yeah, I'll just measure it. There we go. Oh, that must be that far away. You can't do that. You have to. Not all supernovae are the same. Okay, so they don't. As much as they'd like to tell you that they're all standard candles, they're not quite the same. They have slightly different luminosities. So you have to fit them. You have to fit them on a curve, and you have to adjust as well, because there might be some more dust in the way. So you have to try and calibrate and standardize it. Plus, you're making assumptions about how far away it is. How do you measure how far away it is? Well, you look at a host galaxy and you can measure the redshift to that host galaxy. So that also gives you an idea of sort of distance measurement. That means in your calibration of when you take that data and you try and standardize it, what is a standard candle, is I have to be able to remove what I thought the distance was. So that means you're inferring that distance based on a redshift. You might not directly be calling it a redshift, but you're
very
inferring expansion
at some point.
Yes, and that happens
logic.
a lot. Yeah, and the same with even like the surface brightness test, the Tolman surface brightness test. The same thing, right? You can that elegantly proves the idea of an expanding universe. When you look at some of the galaxies and you fit it to the data, then the brightness of those galaxies matches what you would expect actually if the universe is expanding. The problem is that there's a lot of assumptions baked into how do you work out what that galaxy is, because in an expanding universe, a galaxy that is further away is therefore younger. Well, that's not the case if you're in a static universe. Then that you don't know the age, and the age of the galaxy also tells you the size and therefore its luminosity. So there are so many parameters that you bake in that you just take for granted that actually give you that distance measurement, which means that when you And there are people who've done it. So Eric Lerner, for example, reanalyzed some of the Tolman data. And I think in particular, he was looking at the ultraviolet part of it because that gives you a different measurement. And then used his own calibration method based on a non-expanding universe. And he was able to fit it to his data. Now, that doesn't necessarily mean that he's right and they're wrong, but it means that what it clearly shows is that your model can be used to interpret the data and does make a difference to how you interpret that data. Now, people then looked at his data and went, "Oh, that's not fair because you're extrapolating it in a non-expanding universe." Well, hold on, but you did that in an expanding universe. So what's the difference? Like, you know,
They've been wrong about the distance ladder before. There was a big scandal in the 50s. I believe it was the astronomer Walter Beatty, I think. I don't know how you say that last name, but he essentially realized that there was a confusion of two types of Cepheids. And the size of all the distances went up by a factor of 2. I think it was in 1954. So, you know, huge ramifications from just one simple confusion of two types of pulsating stars. So, I mean, there's ample precedent for these kind of things.
well, I think in
flipping.
Halton Arp's book, Seeing, I think it's in the Seeing Red one, he talks about I think it's the Tully-Fisher distance measurement analysis that he did, and he compared it to the redshift. And in his analysis, you can see that there is, as things get further away, because I think the Tully-Fisher only works up to a certain distance, and beyond that, you can't do it anymore. But what he saw is that as the distance got further and further, the gap grew between the Tully-Fisher and, well, in fact, and the redshift. The redshift was giving a distance much further away than the Tully-Fisher one was. So again, I think there are lots of discrepancies in terms of how we measure distance, because of course there are a lot of assumptions. Like I think the Tully-Fisher again uses luminosity of particular types of stars. I think it is. I can't entirely remember how the Tully-Fisher method works, and therefore you have to bake certain things into that. But equally, the idea is that redshift is this pure signal, and that it can only be produced by a recessional velocity. You know, is, I think in some senses flawed, because I think there are other things that can affect that redshift. Yeah, okay. You know, they do account for, you know, the movement of objects within clusters and the rotational as well. But here we're talking about something that you would either consider intrinsic to the object or in the intermediate space is affecting that redshift of the light. And Halton Arp did catalogue quite a lot of these anomalies, even just in terms of redshift, looking at some particular types of stars that are not particularly well explained. That it kind of makes you wonder. Again, the problem with Halton Arp is he's often discredited for a lot of his work because he focused a lot on the idea of quasars ejecting galaxies, and people didn't like that. It's a strange notion, right? That it's quite acceptable to have a point in space which is in itself a singularity, which can quite happily gobble up material ad infinitum. But yet, when we observe these supposed objects, all we observe is material being spewed out. Yeah, that's what we observe. Yeah, but yet we still say it's still drawing material in. And then Halton Arp is actually describing a system where actually it seems almost more natural birthing objects, but it seems foreign because they're not alive, right? So they can't birth things. You know, it would be plasma that turns into a galaxy over time, and it grows and evolves. But essentially, it's related to that original galaxy. And a lot of people discredit his work and say, well, you know, that it doesn't match. When you look at the redshifts, it doesn't match. But the key thing, when you look at the way he describes it, is all based on that host galaxy. So the difference when he analyzed the redshift of the host galaxy versus the quasars that he was looking at, the offset is relative to that host galaxy. So it's not looking just at that object and the other object. It's the delta between those two. And he measured that delta and a multiple stream of objects coming out of it. And you could see a gradual decrease in that redshift in the chain. It could be chance alignment, which is what scientists then say. It's all chance alignment. But as he points out, the chance of it happening so many times is so astronomically unbelievable that he probably should have won the lottery.
I should have bought lottery tickets. I mean, I think that there's something here which is deeply metaphysical. And
Yes.
metaphysical in the sense of what are the rules by which you think the universe operates? And Shiloh's always pointing out that there's this weird, like, quasi-death cult that's emerged around astrophysics and cosmology, where everything is dark matter, dark energy, the heat death of the universe. Everything is speeding towards darkness, stillness, and destruction.
It sounds ridiculous when you say it, but the more you think about it, you're like, it is though. Everything just has this gloomy. I wonder how much it just
weird.
reflects about our own outlook on our
and yet,
present situation.
When you look at the cosmos, how would you describe it?
Magnificent.
Vibrant.
Right.
Awe-inspiring.
Yeah, like I don't want to say electric, but like they're
yeah, for sure.
It feels
Yeah.
I know for people then, but you know what I'm saying. It's all you see is energetic events, high, bright objects, mystery, things that don't make sense. You see strange angles, strange objects, and almost like a continuation. There's like a cycle to things, a pattern that repeats itself over and over again at different scales, at different lengths. And it's funny because like the idea of it being a living universe, I don't think is that crazy. A lot of people don't like that idea that we
Shiloh loves
perceive.
it.
Yeah, I honestly, if you looked at the separate components that are there, which and they work in systems that seem to regenerate themselves over and over, and we accept that there are currents that flow, there are magnetic fields, there is an exchange of energy between objects. Is it so crazy to think that these things don't have, in quotes, a purpose, a function? Maybe function is better than purpose, because purpose is maybe more metaphysical even again. Because then we can talk about consciousness and whether that's all connected to it as well.
I mean, I take like a very strong cosmological principle. I'm like, we should look around the room and see what's going on here, because like that's our best evidence of how the universe works. It's like what's happening in this room right now. And what's happening is like a bunch of atoms have organized themselves into a conversation over Zoom. Like it is completely insane. It's not you're not going to solve that with a wave equation. You know what I mean? And we can't just ignore that is a fundamental piece of what's happening in the universe that we can study most readily, right?
I also have been wondering recently about doing the back of the envelope calculation, where it's like if you took a human being and you blew them up to be the size of the sun, you just kept adding atoms and atoms and atoms until they were the size of the sun. I have a feeling that the laws of physics say that they would look exactly like a sun.
Well, wasn't it Sheldrake that wrote a paper that the sun was conscious? Was it Sheldrake?
I think it was Thomas Gold too.
I mean, there's a great. Have you read Star Maker? I just always have to plug Star Maker anytime we get on this subject. Olaf Stapledon wrote a book
in like the 30s.
It's very old, yeah. But it's so good. It is so good. You only have to read the introduction if you want. If you're not hooked by the first chapter, let it go. But yeah, he just imagines this whole. It's basically this. What would you say? Like a daydream a guy has, essentially. But he imagines this whole network of interrelations where all the mysteries of the stellar motion can be addressed by the fact that they're playing out this drama on this different time scale that's inaccessible to us. And I mean, it's a work of fiction, but it's beautiful, and it really opens your mind up to the possibilities. And honestly, if you look at a star, it's got incredible electromagnetic organization. It seems like it at least has the hardware to be able to do what we're doing right now. I don't know that it does. I can't say that, obviously, but it seems like it would be very difficult to rule it out based on hardware alone, because it's very, very intricate electromagnetic circuitry
and then
going on.
Scale that up to a galaxy. I mean, even more function in a galaxy, because you've got a whole collection of these things, and you have this. I'll call it an engine at the center, and the whole thing is moving. And then, particularly if you then add in Halton Arp's idea that essentially the galaxies birth galaxies. I mean, in terms of stories, like and galaxy or universe evolution models, I think Halton Arp has one of the most beautiful ones that I think exists. You know, I mean, he worked with Hoyle and Narlikar to come up with a modification to their steady state theory, but actually in that version, he misses out some of the nuances of what he writes about in some of his other books, and I think the idea, because essentially one of the problems when you look at a static universe is, well, then surely everywhere we look, we should be seeing all these stars, right? But he envisioned it that there would be these pockets of matter creation that would come and go, a bit like Peratt had this idea of this sort of a cascade event, and Halton Arp describes that you would end up with a seed event. So there'd be some point that would start creating the first seed galaxy in a new area, and that would then birth all these others, which would then birth more, and you'd end up with like a galaxy cluster which would form more galaxy clusters, and they would all sort of connect and spiral together, all within this sort of one domain, and eventually that would then die off, and then somewhere else a new one would form, and within your volume of space, you know, all the objects within it, the redshift would be intrinsic based on that first one. But as you move further out, each new set makes a new one which is based on that. So you end up with this idea of you're creating zones within this one of different ages. Yeah, because he equated the intrinsic redshift to the age of those objects. So as you move further out, you would see younger and younger objects, but you'd end up with these sort of boundary conditions. And when you look at what we see nowadays, you end up with these walls. They describe these walls of galaxies, which they have to then group together into these massive, and they get bigger and bigger and bigger, cluster of objects that almost break the Big Bang model. And that's what he sort of predicts, this idea. And then he says that beyond it, if we ever develop the technology to be able to see far enough, then the objects in the next bubble that would be created would have an offset, which would be a really significant offset in terms of redshift. But if you could detect it, all the ones there would have the same principle, but they would be, from where we see it, it would be a massive redshift offset. And he saw all these different pockets, but the idea was that we would only ever really be able to observe within our own pocket. So what we perceive to be this massive universe is really just this pocket of matter that was created. And if I'm correct, he saw that the origin point for ours was I think it's the Virgo cluster, that it stems from. I believe I might be wrong in there, but I believe he saw that as one of the starting points for this creation. And I think it's a beautiful idea. Yeah, in terms of this idea that you end up with this growing. It sort of matches, I guess, in some sense, what we see, you know, plants and stuff. Though it grows outwards, it spreads, it gets bigger, and then eventually it might die. But the seeds, and it's not a physical seed here that we're talking about. It's some, and he doesn't really ever explain it. But the way I sort of envisioned it is that there is this. Again, if we're talking about what is matter, that it is this vibration in a medium, that there's sudden concentration that happens, I don't know, rupture or something that causes energy to leak out and create matter at that point, which forms that first host galaxy, which then continues that process. It's an elegant, and not necessarily well described in terms of all the equations that sit behind it, but from my perspective, it kind of resonates in terms of a more natural way of looking at it, and perhaps one as well, you know. And you know, okay, they all had problems with their models. They weren't perfect, but I like that idea as an alternative. When you look at other static state theories or infinite universe theories, a lot of them don't, and you could argue they don't have to describe where stuff came from. It's just always been there, right? We just accept that. I find that uncomfortable. It's difficult to deal with that. You have to accept that it's all there, and therefore And you want like you said before, we all want a sort of story, and that's why I kind of lean more towards those that attempt to explain it in some sort of way.
It seems congruent with everything we know about these stable structures in nature too. Like the fact that when atoms are formed, like because you can make atoms right through fission or fusion, right? But they still take on the same shape, right?
Yeah.
It's not like you every time you make an atom, it looks completely different, right? And you can say the same thing about hurricanes or all of these other study. I'm gonna go out on a limb and call hurricanes a structure for the purposes of discussion. Like it has a shape to it and so forth, but like it's not like there's just like a bin of hurricanes hiding out at the North Pole or South Pole, and then one just gets delivered, right? It's informed by the whole collaboration of the rest of the atmosphere under certain conditions, right? So I would imagine that all of these structures, which we see appearing over and over again, are forming and dissolving all the time. That's congruent with everything I know, again, about what's happening in my backyard, like not just with life, but with repetitive structures in nature, right? So,
and they're all connected, right? So even your idea of the hurricane, it's connected to a weather system, which is connected to an atmosphere, which is connected to a sun, which provides the energy. And so therefore, all of these things have a deep connection with each other. We often like to divorce them and not see that there is this greater connection. But I think the same is true when we scale out. It must be true, right? That things repeat themselves. The idea of a fractal universe, that the fact that systems repeat at different scales, we just don't necessarily always recognize the same systems. And that's in some sense that's what Alfvén was attempting to do. He had an auroral circuit. He then said that the same thing would happen with the sun, so he created the sun circuit, which is where this idea that it's a sort of a motor effect that drives the structure in the sun. And he wasn't saying anything else about what the sun was, but just how the magnetic field and the flow of current worked, creating what we see as the solar wind, and how that then connected to the aurora circuit. Then he looked at the galaxies and said that the same principle, again, same idea. You have this turning system, that there is a current that flows through the galaxy and then back through the arms of the galaxy. And then like if you look at Eric Lerner's model, he basically takes that and modifies it in order to produce his plasmoid model, the idea of how he models the equivalent of a black hole or a quasar. And they're all connected. And I think even then, the fact that we see galaxies connected along filaments, and those filaments connect to other filaments, is it so crazy to think that these things aren't somehow, when we say connected, I'm not saying that they're sending messages to each other going, "Oi, give me some more of this, give me some," but the fact that they are part of a system that if you removed one, that system would feel some sort of imbalance in that entire structure. Yeah, that
Isn't
somehow
one of the problems that the universe isn't old enough to accommodate for that to be the case?
Well, that's not true. If it's an infinite universe, we don't have that problem. Sure, the Big Bang has this problem. I'm not sure that we have that problem.
Well, that's one thing I always point out, when people are like, cosmology doesn't matter, who cares if there's a Big Bang or not? I'm like, no, look, it specifies the limitations, right? The boundary conditions under which so many other geological, biological theories are even permitted to be entertained, right? And people don't really realize that. I think they think that cosmology is just this kind of separate, how many angels can fit on the head of a pin kind of discipline.
But you are right. So if you look at the structures, so flipping it on its head, the idea that the universe has formed these massive walls of galaxies so big that actually there isn't time for them to exist is a problem for the Big Bang. So the Kipu structure, which was discovered earlier this year, is one of the largest that is confirmed structures. Now, I would argue that how they actually account for it is a bit strange, but they accept it as this massive structure, and it's 450 megaparsecs long, I think, and that's over I think the limit is 300 that the Big Bang can account for. So it's significantly over that structure. So I'm waiting for a patch for them to solve this. That somehow something magically happens that allowed this to happen. I'm sure there will be some patch that they have to introduce, but it is a problem. Like the Big Bang has a problem, and worse still for the Kipu structure is if it's this big, you would have expected it to have left an imprint in the CMBR. If the CMBR is truly this relic of the Big Bang, yet it doesn't. It doesn't. There's no imprint. So it creates many more problems. But if the idea that these structures are connected probably does require you to remove the idea that the universe is just 13.8 billion years old. That it is a different structure. I mean, in terms of plasma cosmology, they don't hold by the Big Bang anyway. So that there's no need for them to have that. There is no time limit. The galaxies we see can be a whole variety of ages. Just because it's redshift, it doesn't mean that it's younger. It just means that it's further away.
So maybe to wind this down, I can zoom out a bunch and just see if you have a perspective on what it would take to dethrone the Big Bang. Like, would it require a complete administration change, or is there some line by which you can imagine that paradigm shift unfolding?
There is, I think, a physical limit that will become difficult for the Big Bang to explain. At the moment, they're observing galaxies further and further back that are fully matured, that broach on the point that it becomes difficult to explain. Yeah, the ones that they've observed now were originally beyond that point, but they can explain them by saying that they formed quicker than they've patched it. Basically, they've introduced a patch that says, well, they formed quicker than we expected. The problem is that when you look at these early structures, what they don't observe in any of them is the idea. If you look at the models, these beautiful models animations that they produce of how the galaxies formed, it's quite chaotic, right? At the beginning, quite violent, quite chaotic. Lots of mergers, things being drawn out, flung all over the place. Don't observe that. It's not like we look back and see these. What we see when we look back, the further back we look, is these more structured, more beautiful galaxies that just seem to be very similar to the galaxies we know. Yeah, there are other ones of other shapes, but there are these very perfect spherical shaped galaxies, and that doesn't necessarily make sense. Now there will come a point that at the moment you can explain it by introducing patches saying that, well, maybe the processes, we don't fully understand them and they happen quicker. But at some point you come to an event that actually you can't explain that anymore. Now all of a sudden you're entering the point at which there isn't enough time from when the CMBR formed to when the first stars formed to when you form galaxies. And that will create a problem that can't be fixed, because they've almost created a rod for their own back. The CMBR puts a very hard line in the sand that says you can't cross this. And that point creates a timeline forward from that event that says, well, it's going to take that long for you to form the first stars. And from that point, you've got that much time to form the galaxies. And that time now is being pushed back and back and back. And there'll come a point that they go, well, now we need something radically different, or maybe they formed instantly into galaxies. We're not there yet. And maybe our ability to observe that far back won't allow it. But I could see that could be an instant point at which they have to let go. I mean, that's a catastrophic failure if that does happen. But I suspect they might. I think part of the problem is we're so invested in this that people don't want it to fail. And I do wonder whether if observations like that come in, they kind of go, well, let's just put that to the pile over there. We'll look at that maybe next year. We'll defund that project and we'll fund this other project over here.
Or some genius patchwork guy comes in and figures out a way to just stitch it together.
We'll loop it. Yeah, what happens is it actually occurred multiple times. It bounced backwards and forwards. We'll stretch it more. Yeah, more acceleration.
I had a really
more dark stuff.
More dark stuff, absolutely.
Yeah.
I had a really funny experience where somebody on Twitter was posting about black holes, and they're like, it's really incredible how ever since the movie Interstellar, you only see this one shape of black hole. And that's pretty, they kind of, you could tell that their mind was kind of touching it for the first time. And then they were like, that's a little weird. And then just kind of moved on from it. But
I've heard people be like, they predicted the shape of black holes in Interstellar.
oh yeah,
Yeah,
because
that's
they
my
hired
favorite. That's my
mathematicians
favorite.
to produce it. And so it really amuses me the level to which these ideas about impossible objects in the cosmos have worked their way into pop culture
Well,
to
the fact
such a
that
depth.
people actually say, "Oh, but we've observed black holes," and I'm like, "No, we've not observed black holes." And they're like, "Yeah, yeah, there's that image of the donut." I said, "Even if you accept that is an image of a donut, then it's the donut the image is of, and the donut is not the black hole. That's not the black hole. That's the thing that surrounds it.
Do you
It's
ever
the
get tired
accretion
of breaking
disk."
hearts?
No, it's no. It's just frustrating. But this, I mean, again, a lot of it is reinforced by the media, sort of presenting it as these, and I get it because it it sounds fascinating. It sounds interesting. We've imaged the black hole. You're like, "Oh, wow, we've seen we've seen into a singularity. That's just amazing, right? It just sounds so like a film, like a movie, like yeah, and then they see it in Interstellar. It's like, gee, it's real. They proved it, yeah.
It's so
And
funny because I'll like give a lecture going over a lot of these points. Like we'll analyze the black hole image and everything. And we'll go through all this, and then still somebody at the end of the lecture is like, "Yeah, but if there were black holes, like, what would your
yeah,
life be like inside of one or something?" Like I'm just
yeah,
like, all right, I give up.
yeah,
It's
yeah.
too tempting. It's too much fun.
Yeah. Well, I mean, it's a whole system, right? So not only do we have the image of the black holes, but we also have LIGO that's measuring the gravitational waves off the black
Oh,
holes. And I wondered if to close, you couldn't break everybody's heart about LIGO.
it's not
Just a
me. Like
small task.
there were. It was a group of scientists who produced that paper. What's hilarious is that they were not like fringe people. They were mainstream scientists who complained and published a paper that LIGO basically just went, yeah, yeah, and that was it. Just kind of sort of moved on. Yeah, I mean, it's been a long time since I looked at that, but essentially, if you look at the science behind LIGO, LIGO on Earth, yeah, okay, maybe if you took it into space, you might be able to remove some of those noises, but essentially, they're detecting the vibration, and I think it's right in saying the vibration is the size of an atom. I think is correct. That's the vibration that they're looking to detect, and when you look at the data that they receive, it's just like noise. It's just like all this noise, and then they describe that in order to be able to have this as precise as possible, they have to make sure that everything is really still in the environment where they do it, and then they have to subtract the noise that they assume is from like the road and the wind and other things that might be causing vibrations. Because well, hey, the Earth's not still. It's not like you sit here and the Earth doesn't create little tremors, because we are detecting something that's as small as an atom. And when you add all of that up, it's like, wow, yeah. So we can really detect these images. Like, I'm not convinced by it. Like, the fact that those scientists wrote the paper and it was completely ignored, to me, says enough about how LIGO is funded and what's important for them. And
What
the
did they
fact that
write in
they
their paper? Can you refresh my memory?
well, basically they were criticizing their ability to detect their control of noise. They criticized their inability to control the noise, and what they had produced as example images they had analyzed and said, actually, that's not what it looks like. This is what it looks like, and basically pulled the how they attempted to filter the noise apart, saying that effectively by them filtering it, they were in effect forcing waiting, because the part of the problem was they were waiting and waiting. And it's not like when you're looking at the black hole image that you know what you're looking at. So they create essentially a little program that says, look for this image in that noise. And then magically, oh, it creates that image in the noise. with LIGO, they're waiting and waiting and waiting for an event, and then if they hear an event, they're like, "Well, is that an event? Is that enough of an event?" And then, "Oh, that must be enough of an event." And then even worse is when they try and time it with something else. They're like, "Is that the event? That must be the event. There, that one, that one." And I'm sure it's improved since then, because we're talking, this is quite a while ago that they wrote this paper. But the fact is that your ability to detect that level of vibration and assume that you can exclude background vibrational noise is a little bit insane. Like, it doesn't make, even, I would argue, even if you stick it in space, I'm not convinced that you could remove that level of noise, because the structure itself is going to heat up, and then you'll have expansion and creaking, and so I don't know. I'm not convinced by. I'm not saying that gravitational waves may not exist. I'm yet to be convinced that the way LIGO is structured is convincing enough to say that really is data. I think it's such that there's so much noise that you can choose to see data in that noise where it's there. I'll if I can dig it out, I'll send you.
Yeah, please do. That's kind of the case with the black hole images too, right? I think they use like 1 part per billion of the pixel data that they had originally, and so it's like when you're the funny thing is you just don't get away with that in any other science besides these, right? Like, I've worked in laboratories. You're not taking 1 part per billion of your data and getting it past you're not even going to get that past your PI, let alone a reviewer or anything like that, right? So it's a very anomalous piece of the scientific world that takes that as somehow conclusive evidence for something.
But it's more prolific. It's happening more and more. This idea of being able to essentially reconstruct an image out of noise, because that's essentially what you're doing. And what's worse still is it's almost like these AI models where you're training them to understand what image you want from that noise. So you're constraining the model even more by teaching it this is what the image should look like. So therefore only select parts of the data that match that image. And that's dangerous, because that's not real science.
No, and you can take you can take a white noise generator and filter it for whatever frequencies you want, make a chord out of it. Like, it doesn't mean that like Mozart's hanging out in a pile of white noise. It's just,
well, it might be. It might
be. Anything's possible.
Well, man, I think we're gonna have a lot to talk about this summer. I'm really, really stoked we got you on the bill, and I'm really looking forward to hanging out with you in person. It's gonna be good. A few short months. Everybody I'm sure everybody knows your channel, but you make these really beautiful videos where I think that you consolidate a lot of knowledge into a small place, which is extremely difficult to do. And so I love your channel. It's called See the Pattern here on YouTube. Is there anything else that you want to say before we let you go? Anything you want to tell people or encourage people, or where to find you, anything like that?
Well, the same back to you guys. I think what you're doing is different again. Like, I've always wanted to do something like the way you do it, but to me, I get too involved in the detail. To me, it's like I'm always trying to hunt down well, how does this work, or what does that work? And you kind of take the perspective of let's listen to all these different ideas, and let's kind of, and that I think is also much appreciated, that the ability to have a forum where you can discuss controversial ideas, think outside, because I think a lot of it is also about thinking, about being able to talk freely and express ideas. You may not be right in everything you say, but that stimulates the other people's ideas and other thinking, which then builds and builds and builds. And I think that's so important. Like, I mean, for me, the discussion you had with Andre stimulated another part that got me to connect different things together, which have worked into another script that I'm working on. So that's beautiful.
That's really
heck yeah.
Charlotte and I were actually talking about this yesterday, where it really feels like it takes a village to create something where you need the people that focus on the deep details, and you need the people that are focusing on the big picture, and then everybody comes together periodically and cross-pollinates, and then they go off and they keep working, and it's just this. I love what's happening, because the longer that we do it, we just keep finding all of these people that are sort of metaphysically aligned. Like we're all operating inside of this paradigm of like fields, forces, math, magic. And occasionally we'll pluck people out and discover that they're like, no, hey, those people are crazy. Like there's other ways of looking at this. And every time we find one of those people, I just feel like the world becomes more harmonic. It's a really beautiful experience. And we've
It's
been
like,
watching your stuff since we started. And so it's really, really
oh,
cool
thank you.
to finally meet you.
It's like serendipity, you know. I often I can't explain it, and it doesn't make sense for people would look at me. That doesn't make sense that you think that, but I often believe that things happen for a reason. The little things that you hear, connections that you make, are almost like the universe hinting certain things, leaving little trails for you to find and pick up, and you can choose to follow them or you can choose not to follow them. But the more you follow them, the stronger the signal becomes, the more connections that you are able to make. And that I find beautiful in the work that I do and how I do it. I find those all the time, and that it is deeply satisfying to find those connections. I'm not sure that everyone listens to those connections that I make, but in my mind, it's like a journey. I love to be able to try and connect those things together and try and make sense of things that people struggle to explain. And it makes, I guess I don't always succeed in that, but I certainly succeed in my own mind of being able to try and explain that and make connections. And yeah, I think the universe is far more complex and also far more simple than we think in the same sense, which I know doesn't make an awful lot of sense. But I think we overcomplicate how we look at the universe. But I think at the same time, the universe is more intricate in how it works than we think, and we ignore that bigger picture because we don't believe that it can be true. And there isn't necessarily an easy way to explain or prove that that is true, but that's certainly what I believe.
It's beautiful. I'm with you.
It's a wonderful place to end. I really look forward to seeing you at Beyond the Big Bang in Portugal this summer. Everybody should come out. We'll have lots of good conversations. It's going to be, I think
Awesome.
it's going to be a really historic event. And I know I'm hosting it, and so I'm obligated to say that, but I genuinely think that it's going to be a fantastic weekend. And I'm really stoked you're going to be there.
Yeah, a lot of my favorite people too. Just getting in a room together. I'm just really excited to see all of these different thinkers bouncing ideas off each other. So
It'd be interesting to see how we all interact with each other. That I am always very fearful of that. I'll be honest. It's that I have, I guess, imposter syndrome. I never believe that I'm worthy of doing what I do. I always believe that other people are look down on what I do. And I know that's
we were really
wrong.
nervous before the last conference too, for the same reasons. But it was the complete opposite. Like everybody, as soon as people got in the room, like everybody's just like best friends all of a sudden. It was like everybody knew each other forever somehow. It was exactly the opposite of what I was afraid of. So maybe I should stop being afraid of things.
I literally remember conversations with Shiloh before when we were planning the day and trying to figure out how to fill time. I was in full-blown panic because I was like, there's going to be 50 people that show up and sit down in seats, and we are on stage. Like, we don't have a stage show. Like, do we need lights, magic? Like, do I need to be pulling doves out of sleeves? Like, what are we doing? What have we done? And it was, when people showed up, we were still setting up. And so we were finishing, like, everybody showed up an hour early. And they're just kind of awkwardly like standing around the hall as like Shiloh and I are like finishing the last touches. And then slowly I start to hear that there's like people are introducing themselves to each other. Then there's this buzz of conversation. And then all of a sudden people have like printouts of papers that they're exchanging with one another. People have brought books. They're like showing each other passages in the books. And this is even before a single talk has started. And it was such a good experience.
And it's so important too that like along that what we were talking about earlier with the cohesion of the mainstream, it's really important, I think, that we make friends with one another and that we learn how to like find our shared overlap in such a way that we actually have power in opposition to these like institutional paradigms that are obviously they're aged, they're creaky, and they need injection of youth, right? There needs to be new ideas on the table. And I think that we have to kind of at least make some sort of cohesion ourselves as people who are looking at these problems outside on whatever level that is. I think we should all be friends, honestly.
Yeah, no, I don't disagree. I think there are two. If you look at the haters, yeah, there is, although they are of a minority, they're not a vocal minority. They carry a lot of for how small they are. They carry a lot of weight, and I think they're a symptom of a bigger problem that occurs across the entire system, and that is that almost like people don't want to buy into certain things because it's perceived to be not the normal way,
The
and
Graphical
therefore
Wiki told them not to.
well, yeah, that as well. Or Wiki's been rewritten to remove that bit because that's not we don't want that to be what we present. And there's this like formality of what you're allowed to say and what you're not allowed to say, and how dare you criticize this because that's don't you know anything? You like there's one guy, and I often I do take things personally when people write comments, but I have to abstract myself away from those comments, knowing that it's only one individual. But like, there's one person that wrote, "How can you? I've been teaching this for over 30 years. How can you possibly have presented it that way? You know, are you an absolute?" And those sorts of comments, you look at it and you go, what are you on about? And then you kind of realize, if that's true, and you really were a teacher, and you really were teaching this for 30 years, God help your students. You know. Not that I write, I just tend to ignore those comments nowadays because it's just not healthy to engage with them. But you know what I mean? That there is this sort of ingrained idea that either the way that they were taught is the only way that it's possible, or the way that the mainstream consensus work is the only way that's acceptable, and therefore anyone that stands against that is in opposition to it. Whereas what I think is a much better cultural place to be is a place where you can discuss different ideas, and it doesn't matter whether you agree with that idea or not. You're there to listen, because often, and I've said this in the past, it is the bits in the grey that is the important bits. It's not whether the entirety of this, be it black or be it white. It's the nuance of something in the way someone tells you something that actually is the next nugget that takes you on a further quest or a further journey. And it's being able to bring those bits together and being able to foster those discussions to be able to get to those bits that is important. That's what is being stifled in mainstream, and that's what's being excluded. So I absolutely agree that it is about building a community where that is allowed, where that is encouraged, where people can present ideas that might seem a little bit off, and you might not like all of them. Like some of your podcasts, I look at them and go, "No, I'm not that." But that's fine. That's what it's all about. You're not expected to engage with all of it. You're looking at some of them and you're going, "Oh, do you know what? That sounds like an interesting," and I might pick something up. And you do. Invariably, you do. Whether it's a small part in a conversation or a larger consensus topic, that's important, I think. And I think you're right, Shiloh, that is important to create a community that sticks together, that engenders that. It engenders that not just in us as content creators, but engenders it in other people who discuss it with their friends, and then that's a cascade effect. Like I think the problem is that the idea of, can we overturn that current model? I don't see that in the current climate, the way it is, that that's actually possible. But that doesn't mean that you can't create a community that builds the momentum to allow that to happen for future generations. That gives them the thinking patterns, the thoughts, the ideas of how better to communicate.
Yeah, we can make a climate where it's possible to come up with better solutions at the bare minimum. Like, there's no guarantee we will solve these outstanding issues in our day, in our friend circles, in our theory circles, but we can make a climate where it's possible, at least.
Yeah.
And that's a huge step in the right direction.
Yeah. Where it's acceptable that actually a model that you have is not perfect. And it's acceptable to think, actually, rather than presenting it as the only model, that actually you analyze the data that you receive in a more open way that allows you to abstract it to other models rather than constraining it to one model only. And I think that's the problem as well in cosmology, is that the way the data is filtered and processed makes it extremely difficult for other models to be able to actually access the data to see whether it does fit their models, because it's just not possible, or not possible, but extremely difficult, because it's either they hold on to that data and they only give you the process data, or it's sat behind some paywall, or you have to be part of the university to get access to it, and that limits it in so many ways. And I get that, like, what you also don't want is an environment where you end up with 40 billion different models, because everyone wants a different model, and I get people emailing me all the time with, oh, I've got this really great model of this, and I've got this really great model of that. And you're like, that's all very well and nice, but honestly, unless you've got something concrete to give me, oh no, but I've written all this, and a lot of the time it's not written. It's like, they have a slide deck or two, or they're blurb down this whole document list, or I've produced a video on it, and I'm like, I'm really sorry, but I can't, unless you give me something concrete. It's really difficult for me to engage with it. Like,
well,
I've
now
got
with
a
ChatGPT, that's basically like a bottomless pit, right? Like, we're already starting to get summaries where they're like, well, I was talking to ChatGPT about this, and this is what ChatGPT told me, and it's like basically the length of a small novel.
I think it's
thing
more
is,
of it's like an equal opportunity philosophy rather than like an equal outcome, right? It doesn't mean that like every theory is equally plausible. It just means that you're willing to give it a minute to like hear it through. Like, like, show me what you got really, really quick. Like, if it's a good idea, like, I'll lean in further and I'll have more time for it. And I do think science is a strong link problem where, like, who cares about all the bad ideas? Like, they're just not serviceable in the end anyways, and they'll sort of fall to the bottom of the heap naturally. So I'm not too worried about, like, there being this chaos where, like, every theory is equal somehow. It's like, that's not what we're saying.
And I guess if you have enough people in the community, then you have a sort of gravity effect, right? So that if someone presents an idea, then enough people gravitate towards it that actually you get a good indication that actually there is something tangible there. And if they don't, then you kind of know, okay, let's move on to the next one.
Yeah, I think that's exactly it. It's basically creating a space where there's enough people that are engaged with it, that are thinking about it, that have some baseline. We've been doing this segment called Paradigm Drift. I don't know if we told you about it, where we collect volunteers all month, and then we put their names in a hat, and then everybody gets 60 seconds to present a theory, and then we interview them for like 10 minutes afterwards. And it's been really cool because it's very agnostic, and we've given a rubric, which is you have to state the thing that you're trying to solve, you have to state your solution for the thing, and you have to make a clear connection from the problem to the solution. Like, can you do that in 60 seconds? If you can, great, we'll talk about it. It's interesting. People like to hear it.
Like, we still might not buy it at the end of the day, but that's like the bar to entry. Like, that's the cost of the ticket. And if all the fringe theorists could learn how to do that, it would be a much more powerful ecosystem.
Yeah. I think the problem is that sometimes a good idea takes more than 60 seconds to explain. And like, if I look at the structured atom model as an example, like, I suppose maybe you could explain it in 60 seconds, but I would probably have a lot of doubts in that first 60 seconds. Like, yeah, but how do you explain this, and how do I suppose you would still tweak you enough to kind of go, okay, actually, maybe I do. So maybe it does work. Maybe it does. It tweaks you enough
be able to interest somebody, right?
Yeah.
Like, you should be able to interest them in 60 seconds. Like, I just think that
you might not get all of it, but you get enough to go, hmm.
And it's also, I think, an exchange of you have spent enough time on your ideas to formulate them in such a way where there is a short, cohesive presentation that you can make that puts your thesis first, gives the person that you're talking to a 30,000-foot view, so that we can move on from that point, because there are 8 billion ideas out there. And you have to have some way of filtering through them. And so I think that one of the powerful tools for filtering through them is, okay, well, have you thought about it enough to actually be able to explain it very succinctly?
If you have, by the way, you're probably going to anticipate the questions that are immediately going to pop to someone's mind afterwards, right? So you're going to have like multiple layers of abilities to walk someone down into all the details that are necessary, because they're going to ask those questions naturally, because you've already had to ask them to yourself as you figured out the theory and its contingencies with all of the other systems that are involved. So
We're actually thinking of recording a live version of this at the conference, and so you'll get front row seats.
This will be good. I'm looking
see how
forward
it
to it.
works. All right, man. Well, we've gone over 3 hours, so I want to make sure we don't keep you any longer. It's probably getting pretty late over there.
It's 9 o'clock. It's
All
not
right.
too bad.
It's not too bad.
All right. Well, thank you for sitting down with us. It's really cool. I'm glad we finally got to catch up after all these
I
years.
enjoyed
I've
it.
been
So
following
I
you for a long
definitely,
time,
I definitely want to do this again at some point. I think if you're up for it.
yeah, let's
Yeah,
for
of
sure. Let's
course.
do it.
Let's do it.
Yeah.
Some of our best conversations are after we've had people on the show multiple times.
Yeah, I like the idea of it just being free flowing and not necessarily being so. Yeah, it's good. I like it.
We tried to do the script thing when we started, and we were like, we can't do this. This is not us.
I suppose it might work for some structured like discussions. Like I've done shows on was it the Leak Project where I basically presented certain things, but you're almost going through like a presentation, and then you have sort of questions at the end. Whereas this is more like a chat that I often speak to Ido. Not that we do it on camera, we just do it on voice. And you go everywhere. You go, and sometimes you end up going down rabbit holes. You're like, whoa, okay, let's just reverse that conversation and come back here. This is what we were talking about. So it's nice. It's like a more free flowing sort of type of conversation. Enjoyable. I liked it.
Excellent.
Yeah, it's a really healthy way for us to meet friends too, like people that are like, because we're such weirdos. Like we live in the middle of like a rural part of America. Nobody cares about these things that we're talking about here. Next, like it's rare to run into somebody who would even care about the structure of the atom. Or
It's not
something,
like
right?
I go to the shops and someone goes, "Oh, hey, by the way."
Yeah, right.
No.
So this podcast has been such a beautiful blessing in that we can actually meet people who care about the same kind of stuff. So it's really fun to hang out with people who think about this stuff, because they're very rare.
Absolutely.
Yeah, and it also allows you to stretch yourself, to think beyond, take yourself to areas you wouldn't normally consider. Not necessarily that you necessarily want to put that on your podcast all the time, but like these sorts of discussions allow you to think outside the box in a way that you wouldn't normally consider. And particularly brainstorming, you come up, you suggest something, someone else suggests something, and that's a nice dynamic to have, I think.
Yeah. Well, let's do it again. And for now, we should let you go. Have a great rest of your night. We'll talk to you
Awesome.
soon. See you in Portugal.
Thank you very much.
Yeah, thanks, sir. Take care.
Bye.